Imagine you have a twin. You were born on the same day, raised in the same house, shared the same birthdays, and grew up side by side. Now imagine that one of you, let's say you stays on Earth, living a normal life, while your twin gets on a spaceship that can travel close to the speed of light. He flies off into deep space, stays away for what feels like a few years, and then returns. When he comes back, you've aged 20 years, but he's only aged 2. You look older, worn, gray. He looks nearly the same as the day he left. You were born at the same moment, but now you're nearly 2 decades apart. This isn't a dream or a mistake or a metaphor. This is physics. Welcome to the twins paradox, one of the strangest consequences of Einstein's theory of relativity, a thought experiment that breaks our most basic assumptions about time. In simple terms, the faster you move, the slower time passes for you. If you travel at nearly the speed of light, time doesn't tick the same for you as it does for people standing still. This isn't science fiction, it's a measurable fact. It's called time dilation, and we've already proven it. When we send atomic clocks into space, they tick slightly slower than the same clocks on Earth. GPS satellites, yes, the ones helping you navigate your way to the nearest coffee shop, must constantly correct their clocks because of this effect. If they didn't, your GPS location would be off by miles in just a few minutes. That's how real this is. But here's the twist. From your twin's perspective, while he's flying through space, it looks like you're the one moving. So why wouldn't he think that you should be the younger one? Why doesn't this cancel out? You stayed on Earth in one steady motion. He had to accelerate, decelerate, turn around, and come back. Those changes, especially the moment when he turns the ship around to come home, break the balance. That's where the time difference comes from, not from who's moving faster, but from who's changing direction. In real life, this has already happened in tiny ways. Astronauts who have spent time aboard the International Space Station have aged just a fraction of a second less than those of us on Earth. It's small, but it's there. The more extreme the speed and the longer the journey, the bigger the gap. Now imagine this taken to an extreme. Your twin boards a ship that travels 99.99% the speed of light. He leaves for a star 10 light years away, turns around, and comes back. From your point of view on Earth, the whole trip takes about 20 years, but for him, it felt like maybe 2 or 3. When he steps off that ship, he's still young, you're in your 50s. You share a memory of being 10 years old together, but now, standing side by side, you look like his parent. In a way, he has traveled to your future. This is one-way time travel, not to the past, but to the future, and not through magic or imagination, but through speed, through physics, through the fabric of reality itself. If we could build a ship fast enough and survive the trip, we could skip ahead through time. Centuries could pass on Earth, governments could rise and fall, technology could leap forward, and you'd come back as if no time had passed. A traveler from the past, stepping into a future no one prepared you for. But here's where it gets weird. If you can move forward in time, why not move backward? Because physics won't let you, at least not yet. Traveling into the future is allowed. We know how. Traveling into the past, though, breaks everything. It leads to contradictions. If you go back and stop your parents from meeting, do you still exist? If you change something in 1920, do you erase the reason you went back in the first place? These are paradoxes, and they'll come later in this series. For now, let's sit with this. Time is not fixed, it bends. It flows at different speeds depending on how fast you're going. The clock on your wall is not the same as the clock on a moving rocket. Even the act of walking, flying, or standing on a mountain affects the rate at which time ticks. You just don't notice, because you're always living inside your own frame of reference. The twins paradox shows us something deeply uncomfortable. We do not share one time. There is no master clock ticking for everyone. Every person, every particle, every object has its own clock, its own path through space and time, its own private rhythm. And that means you could live in a world where people born at the same moment die a century apart. So next time someone says, we all have the same 24 hours, maybe remind them, that's not exactly true. We don't all move through time the same way. Some of us leave it behind. Some of us stay and watch it pass. And some of us are waiting to be caught by it. It started on an online forum. No headlines, no breaking news, just a post, anonymous, clumsy, and strange. The username was simple, Time Travel 0. Later, he began signing his posts as John Titter. He claimed to be a soldier from the year 2036, sent back in time to retrieve a specific piece of 1970s technology, not to save the world, not to stop a war, but to recover an IBM 5100 computer, an old, obscure model that, according to him, could debug legacy systems in a way no other machine could. At first, no one paid attention. But then he answered questions, in detail, technical, historical, specific. He explained time travel as if it were real, routine even. He described the machine that supposedly took him back. He posted diagrams. He explained the physics. He said his machine was installed in a 1967 Chevrolet Corvette and powered by two miniature black holes. He described the distortions in gravity it created, the way time shifted around the vehicle, the intense gravitational fields that bent space and time like fabric around a weight. People were skeptical, some laughed, others asked more. And that's when things got weird. Because John Titter began predicting the future. He talked about a civil conflict in the United States starting in the mid-2000s, about a global nuclear war in 2015 that would kill millions, about a fractured future where America was no longer a superpower but a collection of regional governments. He described future technology, changes in culture, the evolution of the internet, and even political tensions that at the time seemed far-fetched. But some of them weren't. He mentioned the growing instability of Russia, the tension with China. He described the vulnerability of centralized systems and the rise of decentralized data. He predicted that people would soon carry devices that gave them access to constant information but made them more isolated. That news would become fragmented. That truth would splinter into perspective. He warned about a future where people stopped trusting each other, not because of violence, but because of overwhelming information. And suddenly, people weren't laughing anymore. But here's the thing, some of his predictions never came true. No civil war, no nuclear apocalypse, no mass time travel program in the early 2000s. So skeptics pointed and said, see, he's just a hoax. But John had an answer for that too. He said he wasn't from our timeline. According to him, every decision, every movement, every particle branching ever so slightly creates a new divergence, a new version of history. When he traveled back to the year 2000, he didn't land in his past. He landed in ours, a timeline close to his own, but not identical. In his version, certain events unfolded one way. In ours, they shifted. That idea, called the many worlds interpretation, is a real theory in quantum physics. It suggests that every quantum event creates a branching universe, one in which the cat lives and one in which the cat dies, one where you read this story and one where you didn't. John Titter said his presence here wasn't to warn us, it was to do a job, retrieve the computer, go home, nothing more. And then he vanished. In March 2001, the post stopped. The username disappeared, no more predictions, no more diagrams, just silence. People have spent decades trying to figure out who he was. A hoax, a coordinated performance art project, a brilliant troll, a marketing stunt. No one has ever proven anything. The IP addresses were masked. The posts were made from random locations. The timeline was clean. And the IBM 5100. Years later, real engineers confirmed that it did, in fact, have an undocumented feature allowing it to emulate older systems. A feature unknown to the public at the time of John's posts, and something only a few insiders would have known. That was real. So what do we do with that? Was it all just an incredibly lucky guess? A story too perfectly weird to be true, but too accurate to dismiss? A man from the future who left breadcrumbs not to warn us, but to test something, maybe even to observe. See, the most unsettling part of the John Titter story isn't whether he was real. It's that you can't prove he was. He didn't ask for money, he didn't try to sell books, he didn't try to change the world. He just told his version of the truth and left. And if you believe in even the smallest possibility of parallel timelines, if you believe that time branches and folds in ways we don't yet understand, then one version of Earth somewhere did see those wars. Did need that IBM 5100, did send someone back. Maybe not here. But somewhere a man really did climb into a car, powered by a miniature black hole, and pressed a button. And maybe he arrived here by mistake. Or maybe we were the experiment all along. In the fall of 1943, something strange was said to have happened in the Philadelphia Naval Shipyard. According to the story, the U.S. Navy was working on a top-secret project, something to make ships invisible to enemy radar. They called it Project Rainbow. The idea was based on electromagnetic fields, cloaking, and experimental physics that were decades ahead of their time. But what came out of it, if the legends are to be believed, was not just radar invisibility, but something far more disturbing. They said the ship disappeared completely. Not off radar, not off sonar, but gone. Physically gone from sight, from space, from time. The ship in question was the USS Eldridge, a destroyer escort vessel docked quietly in the harbor. According to the tale, on October 28, 1943, the experiment began. Powerful generators were activated, magnetic coils lit up, a greenish fog surrounded the ship, and then, in a flash of blue light, the Eldridge vanished. Some claimed it was seen, briefly, off the coast of Norfolk, Virginia, 300 kilometers away, before vanishing again and reappearing back in Philadelphia. And the crew, they were never the same. The stories say that some sailors were found fused into the metal of the ship. Others had gone mad, screaming about distorted space and lost time. A few were said to have vanished entirely, never returning from wherever the ship had gone. One man, they claimed, kept randomly disappearing in front of witnesses, phasing in and out of reality like a glitch in the world's code. And then, as quickly as it came, the project was buried. Officially, the Navy denied it all. The Eldridge, they said, was never in Philadelphia on that date. There was no such experiment, no such project. The logs showed routine operations. Everything was normal. But the story didn't die. It came from a man named Carl Allen, who later used the pseudonym Carlos Allende. He sent letters to scientists, to military personnel, to UFO researchers, claiming he'd witnessed the experiment firsthand. He talked about Einstein's unified field theory being used to bend space and time. He said the government had unlocked something they couldn't control. Over the years, the legend grew, books were written, documentaries made, witnesses appeared, then vanished. Some claimed it was a cover-up of early teleportation technology. Others said it was an accidental breach into another dimension. A few believed it was a failed attempt to travel through time. The science behind it. Mostly speculation. There's no known method today or in 1943 that could make a 1,200-ton warship disappear. But the physics community doesn't entirely dismiss the idea of warping space. In theory, if you could bend spacetime enough, like folding a sheet of paper to make two distant points touch, you could move an object without crossing the space between. That's the concept behind wormholes, after all, but it requires energy on a cosmic scale. Nothing we've ever come close to. Still, the timing of the story is strange. It came just as World War II was reaching its peak, just as the world was discovering nuclear fission, radar cloaking, and stealth technology, just as Einstein's theories were becoming tools for war, just as secrecy, misinformation, and psychological operations became weapons themselves. And that's what makes the Philadelphia experiment so haunting, not whether it happened, but how easily it could have happened. The idea that governments might run dangerous, uncontrolled tests in pursuit of military superiority, that they might erase failures or silence those who saw too much, that's not science fiction, that's history. And the deeper fear isn't about one ship disappearing. It's that we may have already opened doors we don't understand. That somewhere, in a moment lost to classified files and altered records, something broke, a rule, a law, a seam in space that was never meant to be touched. And maybe the people involved never meant to step through it. But they did. And ever since then, the story keeps coming back, not because it's proven, but because it refuses to go away. Like a shadow at the edge of recorded history, just far enough to doubt, but close enough to fear. So the next time you hear about a ship that disappeared, or a person who vanished and reappeared in the wrong place, or a secret file buried under decades of red tape, ask yourself, is it really just a myth? Or did someone, somewhere, actually see what happens when time folds in the wrong direction? You step into an elevator, the door closes. There's no window, no sound from outside, just silence and a slow, gentle pressure beneath your feet. It feels like you're moving upward, but how do you know? Maybe you're in a building, going to the 10th floor. Or maybe you're not on Earth at all. Maybe you're floating in deep space, far from any planet, inside a box that's being pulled upward by a rocket engine. The feeling, the pressure on your feet is exactly the same. You feel heavier, grounded. But is it gravity or is it acceleration? You can't tell. And that was Einstein's point. In 1907, years before he finished his theory of general relativity, Albert Einstein had what he called the happiest thought of my life. It wasn't about stars or black holes. It was about elevators. He realized that inside a closed box, there's no physical experiment you could do to distinguish between uniform acceleration and the pull of gravity. In other words, gravity and acceleration feel the same. That may sound small, but it was revolutionary. Because if they feel the same, maybe they are the same. Maybe gravity isn't some invisible force pulling things down, like Newton believed. Maybe gravity is just what happens when something follows the curves and slopes in spacetime itself, just like a marble rolling along a stretched rubber sheet. Einstein's elevator was a thought experiment, but it cracked open the door to a new way of seeing the universe, not as a static stage where events happen, but as a dynamic fabric, flexible, stretchable, and alive. And once you realize that spacetime can bend, you realize that time can bend too. Now we get to the strange part. Imagine two elevators. The first one is hanging in a building on Earth, pulled down by gravity. The second one is drifting in space, then suddenly begins to accelerate upward, fast. Inside both elevators, a person drops a ball. In both cases, the ball falls to the floor at the exact same rate. The person can't tell whether they're feeling gravity or thrust. In physics, we say the two situations are locally indistinguishable. That principle is called equivalence, and it's the foundation for general relativity. Now follow this idea further. If gravity is the same as acceleration, and we know acceleration affects time, then gravity must affect time too. And it does. Time moves slower in stronger gravity. This isn't metaphor, this isn't theory, this is measurable. Clocks placed at different altitudes on Earth tick at slightly different rates. Your head ages faster than your feet. A person living on a mountain gets a few more nanoseconds of time than someone at sea level. The difference is tiny, but in the language of physics, it's real. Einstein's elevator didn't just help us understand gravity, it changed how we think about time itself. Suddenly, time wasn't absolute. It could stretch, compress, twist. Depending on where you are, how fast you're moving, and what gravitational field you're in, your experience of time shifts. Not as a trick of the brain, but as a fact of nature. Now imagine building on this. If you can manipulate gravity, you can manipulate time. This is why black holes, with their intense gravitational pull, slow time dramatically. From the outside, anything falling in appears to freeze at the edge. For someone falling in, time feels normal, but to the outside world, their clock is crawling. And what if you could reverse the effect? What if you could create a space where gravity isn't just slowing time, but turning it around? That's where the idea of time travel begins, not with science fiction, but with elevators. With a single question: if I can't tell the difference between falling and flying, maybe space and time aren't separate at all. Maybe they're one thing. Maybe we live not in time, but through it. A direction, a slope, a path you can climb or fall down. Einstein never built a time machine. But his elevator gave us the blueprint, not in gears or engines, but in ideas. The kind that shift everything just enough to glimpse what's been hidden the whole time. That time itself is local, and we've been riding its currents without even knowing. It wasn't supposed to exist. It wasn't in any textbook, military archive, or declassified file. But in 2002, an Italian priest named Father François Brune published a book claiming that deep inside the Vatican, hidden away from the public, there was a device, a machine that could see through time. They called it the Chronovvisor. It wasn't a portal, it didn't let you travel, it let you watch. Like a television for the past. According to Brune, the device was built in the 1950s by a team of scientists, including the famous Italian physicist Enrico Fermi and a Benedictine monk named Father Pellegrino Ernetti. Ernetti, a respected scholar of ancient music, claimed that the machine could capture images and sounds from any moment in history by tuning into residual energy left in the fabric of spacetime. He said that every event, every word spoken, every movement made leaves behind a trace, like radio waves, and the Chronovisor could detect them, decode them, display them. He said he had seen Jesus. Not a vision, not a dream, but an actual visual recording, Jesus speaking to a crowd alive in motion. Ernetti claimed to have watched ancient Rome, listened to lost plays of Sophocles, even heard conversations from long-dead popes. The Chronovisor, he said, was the ultimate recorder. Time was a movie, and they had the remote. He even published a photo. It showed a man on a cross, his head tilted, eyes closed in agony. Ernetti said it was a still frame from the crucifixion, that they had watched it unfold with their own eyes. Critics immediately tore it apart. The photo, they said, looked suspiciously like a statue from an old church, the science behind the machine pure fantasy. There was no known method to reconstruct historical events from the echo of their energy, and the Vatican, silent, no comment, no confirmation, no denial. But Ernetti never backed down. He insisted it was real. He said the Vatican had dismantled the machine after realizing its power, fearing it could be misused. Imagine the chaos, he warned, if governments could see anything. Proof of betrayal, secrets from the past, private moments made public, wars could be rewritten, history could be weaponized. So they locked it away. Brune claimed that parts of the Chronovisor still exist, hidden deep within the Vatican archives, not destroyed, just dormant. The story reads like science fiction, a religious time TV built by physicists and monks, lost to secrecy, but the questions it raises are very real. What if time doesn't disappear? What if it simply accumulates? Like echoes in a canyon, like fingerprints on glass. What if every moment you've ever lived still exists, somewhere, imprinted on spacetime like grooves in a record? And what if the universe is constantly recording you? Not consciously, not for judgment, just mechanically like a passive witness. Every conversation you've had, every movement, every choice, stored. Not gone. Just inaccessible. Unless someone, somewhere found the key. The Chronovisor isn't taken seriously by mainstream science. There's no published design, no proof, no peer-reviewed explanation for how it could work, but the fear behind it, that feels real. The fear that the past isn't truly behind us. That there's no such thing as what's done is done. That the truth, your truth, everyone's truth, is still out there, playing in a loop, waiting to be tuned in by the right machine. And if someone could build that machine, what would they do with it? Watch the moment Caesar died, see the birth of your great-grandmother, uncover a crime no one knew happened. Or worse, what if they watched you? And what if someone already is? Start with a cylinder, not a small one. This one is massive, infinitely long in theory, dense, rotating at near the speed of light. A pillar through space-time, spinning so fast it drags the very fabric of reality around it. This is the Tipler Cylinder, one of the most elegant and terrifying ideas in theoretical physics. First proposed in 1974 by physicist Frank J. Tipler, it's not just a machine, it's a loophole in time. According to the equations of general relativity, if you take a supermassive cylinder and make it rotate fast enough, the space around it begins to twist. Not just bend, twist, like water swirling down a drain. This dragging effect, called frame dragging, creates something unusual, a loop in time. A closed, time-like curve. What that means in plain language is this. If you get close enough to the cylinder and you follow a very specific path around it, you could end up back where you started, not just in space, but in time. You could travel into your own past. It doesn't look like a time machine. No flashing lights, no portals, no DeLorean, just a giant, spinning object that warps the rules of causality by its very presence. The logic is simple, but the consequences aren't. If you could travel in a loop through time, you could meet yourself, or stop yourself, or create a paradox. You could cause an event that made you come back in the first place, or prevent it. You could undo the very reason you're there. And yet, mathematically, the Tipler cylinder works. Under certain conditions, the equations of general relativity allow it. But here's the problem. To build one, you'd need materials with infinite density, or at least more than anything we can imagine. Some estimates suggest you'd need more mass than exists in the observable universe. And even if you had that, you'd need to spin the cylinder at nearly the speed of light without it tearing itself apart or collapsing into a black hole. In short, it's impossible, but not forbidden. And that's the unsettling part. Physics doesn't say you can't, it just says you probably won't. Some have speculated about workarounds, wormholes, exotic matter, other geometries, but the Tipler cylinder remains the cleanest, most direct path to engineered time travel within known physics. A rotating object built to abuse the laws of relativity to slice through time like a blade. And maybe we don't need to build one. Maybe they already exist. Imagine that somewhere in the universe, a collapsed star, not quite a black hole, rotates at just the right speed. Maybe two of them, maybe a neutron star paired with something even stranger. The gravity, the motion, the spin, it could all come together accidentally. A natural Tipler cylinder hidden in space. And if you found it, you could enter at just the right angle, follow the right arc, and suddenly you're not in the future anymore, or the present, you're in a loop, one that never should have existed, one that no one can follow you into, one where you're completely, cosmically alone with yourself. Because time loops don't have exits. They just repeat, over and over, until something changes. And what if that's already happened? What if some civilizations did build one, or found one, and vanished into themselves, looping endlessly, lost in their own timeline, never to escape? And what if someone is watching the sky right now, looking for something that doesn't make sense, and finds it? A pattern that repeats, a signal that folds back, a light that flashes in a perfect cycle, not because it's broken, but because it's circling time itself. Would we understand what we were looking at? Or would we mistake a time machine for just another star? And if someone waved to us from the past, could we even wave back? Kurt Gödel wasn't a physicist, he was a logician, a man who proved through sheer thought that no system of logic could ever be complete, that some truths would always lie beyond proof, that some answers would always escape us. And then he turned to time. In 1949, just a few years after Einstein published his theory of general relativity, Gödel did something strange. He took Einstein's equations and asked a question no one else had dared. What happens if the entire universe is rotating? Not a planet, not a galaxy. The entire universe. He ran the math, and what he found wasn't just a curiosity, it was a crack in reality. In Gödel's rotating universe, the fabric of spacetime twists, not like a sheet, but like a spiral, and in that spiral, something terrifying appears. Closed time-like curves. Paths through space that loop back in time. In this universe, if you traveled far enough and curved your journey just right, you could end up in your own past. You could witness your own arrival, send a letter before you were born, undo events, cause your own existence, or erase it. And it wasn't fiction, it was math, precise, clean, solved within the very framework of Einstein's most sacred work. Einstein didn't like it. He respected Gödel deeply, they were friends, but the idea disturbed him, not because it was wrong, but because it was. Gödel's model satisfied all the conditions of relativity, it just didn't satisfy common sense. In Gödel's universe, the arrow of time was no longer a straight line, it was a spiral staircase, and if you knew how to walk it just right, you could climb backward. But the implications didn't stop there. If such a universe could exist, what does that say about our universe? Is time truly linear here, or are there hidden curves too subtle to detect, too vast to follow, that could still allow for loops? Could the cosmos, on the largest scale, be rotating in a way we haven't yet measured? Most cosmologists say no. Observations of cosmic background radiation suggest the universe is flat and isotropic, not spinning, not twisted. But Gödel never claimed his model was real, only that it was possible. And sometimes possibility is scarier than reality. Because it means that the laws of the universe, the very ones we trust to build rockets, GPS, and nuclear power, allow for something as strange and unstable as time travel. That built into the blueprint of existence is a trapdoor, a way out, a way back. We don't know what it would feel like to move along a closed time-like curve. We don't know what happens to memory, identity, or causality. We don't know if you'd arrive whole or fragmented. But the math says you can. And math, especially Gödel's math, doesn't lie. In fact, that's what makes Gödel's work so haunting. He proved that truth exists beyond proof, that some things are real even if they can't be shown, that systems, even perfect ones, contain their own limits. And then he showed that time, too, might be one of those systems. Incomplete, looping, unstable. A suggestion, not a rule. So what do you do with a universe like that? Do you look for the spiral, try to trace the curve? Or do you look behind you and wonder if someone's already made the loop, and they're just waiting for you to catch up? It started with a locked drawer in an old university lab in Kazan, Russia. The kind of place with rusted filing cabinets, yellowed papers, and names no one remembers. But inside that drawer were notes, handwritten, dense, strange. The title scrawled in Cyrillic read, Temporal Distortions. The author, a man named Andrei Yurov. There's almost nothing about him in official records, no photos, no public lectures, no published papers, just these notes. And one faded ID card from the Soviet Academy of Sciences, dated 1981. The content of the notes, that's where things shift. They describe a series of experiments involving an isolated chamber, something like a Faraday cage, but much thicker, lined with lead, copper coils, and strange mineral composites. Yurov claimed he could generate an internal magnetic field powerful enough to distort atomic resonance, not enough to affect space, but enough to bend time. According to the notes, he tested it on small organisms first, insects, mice. When placed in the chamber, they became sluggish, unresponsive. Their heartbeats slowed, their metabolism dropped. After a 10-minute exposure, they emerged as if no time had passed inside, while outside the clock had moved forward. Time, Yurov wrote, had stretched. Then he escalated. He built what he called a capsula, a human-sized chamber sealed from all external forces. In one entry, he describes locking himself inside. He sets a mechanical timer, activates the generator, and waits. He describes hearing a hum, then silence, then a deep pressure in his ears, like falling but without motion. When he stepped out, his assistant looked panicked. 30 minutes had passed outside, but inside he felt only 5. He describes confusion, nausea, then clarity, a sense that the world felt slightly off, not visibly different, but subtly wrong, as if a conversation had happened that shouldn't have, as if someone remembered something differently than he did. Then come the diagrams. Rotating fields, counterspinning magnetic layers, spiral trajectories through spacetime, handwritten equations that border on madness and genius, equations involving proper time, energy curvature, and a term he calls the shadow of time. Yurov believed that time isn't a line. He believed it's a density, a medium that can be compressed or stretched, and just like you can pressurize air in a chamber, you can pressurize time, trapping it, altering its flow. The last note is the strangest. He writes about a second test, longer, more precise. He enters the chamber again, this time for what he estimates will be 1 hour inside. The logs show the chamber was sealed at 4:17 p.m. It was opened again at 4:39 p.m. Andrei Yurov was gone. No trace, no body, no disturbance, no malfunction, just an empty chamber. The door was still locked from the inside. In the margins of the final page, he had written something hastily. If the ratio holds, I will return on the 5th day. If not, remember me in the fold. He never came back. No one knows what the fold meant, or if he miscalculated, or if the chamber worked too well. Maybe he went too far forward. Maybe he's still on his way back. Maybe he never existed at all. The Soviet program he worked for, if it ever existed, was shut down. No one claims the project now. His assistant disappeared. The lab was dismantled, but the notes remained, eventually bought at a university auction by a physicist cleaning out old archives. He thought they were science fiction until he ran the math and found that some of it held up. We don't know what really happened in that chamber, but the story of Andrei Yurov is different from most time travel tales. It doesn't come from TV or forums or myths. It comes from silence, from a set of notes no one was supposed to find, from equations buried in forgotten folders, from a man who walked into a box and didn't come out. And maybe the most terrifying part is that the experiment failed. But that it worked too well. And somewhere out there, someone is still waiting for the clock to catch up. Imagine you're walking down a hallway. It's long, dimly lit with no doors, just a straight path. At first, it feels endless. But then, after a while, something strange happens. You see a shape ahead, a figure. It's someone walking toward you. You slow down, so do they, and then you realize. It's you. Not a mirror, not a trick. It's you from a few minutes ago, walking the same hallway in the other direction. Somehow, without knowing it, you've walked a path that brought you back to your own past. The hallway isn't straight after all. It loops, not in space, but in time. This is the idea behind a closed timelike curve, or CTC. In physics, a timelike path is the kind of path anything with mass takes through spacetime. It's your timeline, from birth to death. A closed timelike curve is when that path loops back on itself so that your future intersects with your own past. It sounds impossible, but in Einstein's general relativity, it's not. In fact, multiple solutions to his equations allow for them. The Tipler Cylinder, Gödel's rotating universe, traversable wormholes, even certain models involving cosmic strings or black holes with unusual spin, they all lead to the same strange possibility that the geometry of spacetime itself might allow you to double back, that the universe might have pockets where time is not a line, but a loop. The implications are enormous and terrifying. With a closed timelike curve, you could send a message into your own past, or meet yourself, or change something, or watch something unfold again and again. And that leads to paradox. The classic example, you go back in time and destroy the machine that allowed you to go back in time. Now what? How did you ever go back in the first place? Or worse, what if you go back and nothing changes? What if you try to save someone or stop something, but no matter what you do, the outcome remains the same, not because you're not trying, but because the loop won't let you? Some physicists argue that this is how reality protects itself, that if closed timelike curves exist, they come with built-in rules. The past is fixed. You can visit it, but you can't change it. Every attempt to create a paradox simply leads you into the events that caused it in the first place. This idea is called Novikov's self-consistency principle. It says, time is flexible but not stupid. You can't break it. You can only discover that you were always part of the loop. Others disagree. They believe that once you enter a CTC, causality becomes optional. That timelines can split, fork, multiply, that each attempt to change the past creates a new branch of reality, one where your actions ripple outward, unrestricted. There's no consensus. Only equations and questions. Some researchers believe we'll never be able to access CTCs, if they even exist. Others think that quantum effects would destroy them before they could form, but here's the haunting part, we wouldn't know if we were in one. Think about it. If time loops and you're caught inside that loop, your memory might reset every cycle. You'd never remember the last time through. You could be reliving the same hour, the same year, the same lifetime, over and over, with no way to notice, no way out. And what about the universe itself? If closed timelike curves are possible, could the entire cosmos be inside one? Could the Big Bang be not the start of time, but its end, looping back again and again? A perfect cycle of birth and death, expansion and collapse, playing on repeat for eternity. We don't know. But if time has a shape and that shape can curve, then maybe, just maybe, someone has already walked that curve. Maybe that hallway isn't a metaphor. Maybe you've already met yourself. You just don't remember the last time. There's a small town at the far end of Long Island, New York, peaceful, quiet, surrounded by dunes, sea air, and weathered homes. But at the edge of this town sits a military base, abandoned, rusting, eerie. It's called Camp Hero. And according to one of the strangest stories in modern conspiracy history, this place was once the site of a secret experiment in time. They called it the Montauk Project. It allegedly began in the 1970s, a spin-off from the infamous Philadelphia experiment. Where that experiment supposedly focused on teleportation and invisibility, Montauk was about mind control and eventually time manipulation. The story comes from Preston Nichols, an electrical engineer who claimed to have worked on the project. He said that in a hidden underground facility beneath Camp Hero, the U.S. government built a powerful transmitter, something that could send signals directly into the human brain. They started by trying to influence thoughts, emotions, and dreams. But then, things went further. Much further. Nichols claimed they discovered that when the human mind was connected to the machine, particularly the mind of one gifted boy named Duncan, something opened. Not just a mental gateway, a literal tear in space-time. He described time tunnels, vortexes, portals that appeared in the air, visible, walkable, controllable. Through them, people could be sent to other places, other times. Sometimes they came back. Sometimes they didn't. Nichols said the team conducted experiments where subjects were sent as far back as ancient Egypt or thrust forward into unknown futures. He claimed they tried to erase people from history, wipe memories, and even bring objects back from different timelines. It sounds absurd. It probably is. But parts of the story linger, too detailed to ignore, too strange to explain away entirely. Camp Hero is real. The base is real. There are sealed bunkers, blocked-off elevators, thick cables trailing into empty rooms, and the government has been remarkably quiet about what was done there. No one has officially confirmed or denied any of it. In one version of the story, the project spun out of control. Duncan, still hooked into the machine, supposedly manifested a creature from his own mind, a monster that appeared in the facility, began destroying equipment, and forced the entire project to be shut down. The machine was dismantled, the records destroyed, the people scattered. But what if some of them remember? Preston Nichols described years of fragmented memories, missing time, dreams of other lives, unexplained knowledge. He claimed the government deliberately wiped the minds of those involved, leaving them with only flashes. And maybe the story would have faded, just another strange tale, whispered in corners of the internet, except for one thing. Years later, a popular show on Netflix, Stranger Things, would borrow many of these elements. The government lab, the child with special abilities, the hidden base, the portal to another world, the monster from the mind. They didn't hide the inspiration. They called it Project Montauk in the show's early drafts. So here we are in a loop of fiction and myth and maybe truth. The Montauk Project remains unproven, unsupported by science, lacking evidence. But it's not about the evidence. It's about the idea that somewhere beneath the ground, behind concrete walls and forgotten doors, someone may have tried to reach through time, not with equations or spaceships, but with thought. That the mind itself could tear a hole in the timeline. And that we may have already walked through it and just don't remember what was on the other side. Imagine standing on the edge of a great dark sphere, silent, unmoving, perfectly black, a black hole. From where you're standing, it doesn't look like much. No swirling lights, no dramatic whirlpools, just a void in space where no light escapes. But the closer you get, the stranger things become. Because time starts to break. This isn't science fiction. It's one of the most well-understood predictions of Einstein's general relativity. Around every black hole is a boundary called the event horizon, a point of no return. Cross it, and not even light can escape, but you don't need to cross it to feel its effects. Just approaching it is enough to slow your time down. This is called gravitational time dilation. The stronger the gravity, the slower time passes, and black holes are the strongest gravity wells we know, so near 1 second stretch, minutes turn elastic, hours warp. Here's how it plays out. Imagine you're orbiting close to a black hole in a sturdy, hypothetical spaceship. From your perspective, everything feels normal. You're reading a book, drinking coffee, talking to your crewmate, but far away someone is watching from a safe distance, a friend monitoring you from their own ship. To them, you're moving in slow motion. Your gestures are sluggish, your voice is warped, your time has slowed down. Now imagine spending a few hours in that orbit, close to the edge but not falling in. You finish a chapter of your book, you stretch, you head back to the control panel, maybe 4 hours have passed for you. But for your friend, it's been 6 months. You return and the world has changed. Messages flood in. People you knew are older. Events you never witnessed have already happened. While you sat there, calmly looping near the horizon, the universe raced ahead without you. And if you get closer, time slows even more. At the edge, at the very lip of the event horizon, time almost stops entirely. From the outside, it looks like you're frozen, stuck in place forever, never quite crossing. But from your point of view, you're still moving, still breathing, still falling. You just don't realize that the rest of the universe is sprinting toward the future at light speed while you crawl through seconds. This is not theoretical, it's real. We've observed these effects on a smaller scale near Earth. GPS satellites orbiting our planet must account for both their velocity and the weaker gravity at their altitude. Their clocks tick faster than clocks on the ground. Without correction, GPS would drift by kilometers each day. So black holes are just the extreme version. They are time machines, but only in one direction, forward. You can't use them to go back, but you can use them to wait out the universe, to jump ahead, spend a week near the edge and return to find decades have passed, not as a ghost or a traveler from myth, but as yourself unchanged. To the world, you were missing. To you, it was just Tuesday. And this opens a strange possibility. If we could build ships tough enough to survive the gravity and navigate the radiation, we could place people in orbit near a black hole, effectively freezing their time. Emergency survivors, data carriers, witnesses waiting for a future where technology is ready for them. Or maybe someone already has. What if the oldest beings in the universe aren't dead, but waiting? What if intelligence from another age slowed itself near a black hole, planning to emerge in the far future, when civilizations like ours finally catch up? Or maybe you're the one who waits. Maybe one day when the Earth is fading and the sky is full of quiet stars, you'll choose to orbit the darkness, to watch time stretch, to enter sleep and wake up in a century you'll never recognize. Not because you traveled through space, but because you fell near something that doesn't care about time at all. Picture two pieces of paper. On one, you draw a dot labeled A. On the other, a dot labeled B. The shortest distance between them, in ordinary space, is a straight line across the surface. But what if you could bend the paper, fold it in half so the two dots touch? Now you're not moving through space, you're moving through a shortcut. That's the idea behind a wormhole. In theory, a wormhole is a tunnel through spacetime, not just from one place to another, but potentially from one time to another. A bridge, a passage, a fold in the fabric of reality that lets you go from here to there without crossing the space in between. The idea comes straight from Einstein's general relativity. In fact, the first known solution resembling a wormhole was discovered in 1935 by Einstein and physicist Nathan Rosen. They described it as a bridge between two regions of spacetime, what later became known as the Einstein-Rosen bridge. At the time, they didn't think it had physical meaning. It was a mathematical curiosity. But years later, physicists began to wonder, what if it was? What if it was real? The structure of a wormhole is simple in theory, but nearly impossible in practice. You need two mouths, two connected spheres in space, and a throat between them. If you could keep that throat open, you could step into one mouth and instantly emerge from the other. Go in through a tunnel in your garage. Come out on a beach in 12th century Japan. Or in a bunker 50 years from now. Or on a spaceship orbiting a dying star. But here's the catch: wormholes collapse almost instantly. The throat pinches shut before anything can get through. To hold one open, you'd need something called exotic matter, a form of energy with negative mass. Not antimatter, not dark matter, something stranger, something we haven't found. And even if we did, things get weirder. Let's say you somehow stabilized a wormhole, and then you took one of its mouths and moved it. You accelerate it near the speed of light, fly it around for a while, then bring it back. Because of time dilation, the moving mouth will have experienced less time than the one that stayed still. You've just made a time machine. Not a metaphorical one, a literal one. Now the two mouths are out of sync. If you enter the older mouth, you come out the younger one in the past, step back through, and you return to the future. Not all of spacetime, just that private tunnel, just that closed circuit. This doesn't break relativity, it follows it. But it does break our brains. Because now you have a way to send information or people backward in time. You can create loops, messages that arrive before they were written, warnings from tomorrow, interactions with versions of yourself that haven't yet happened. And then the paradoxes begin. If you send back the instructions for a time machine and your younger self builds it, who actually invented it? If you go back and prevent a disaster, what reason did you have to go back in the first place? Some physicists believe the universe will prevent this, that any time loop collapses into consistency, that events always close on themselves, forming causal loops where everything that happens was always meant to. Others think the moment you do this, reality splits. You create a new timeline, a new world, one where your actions ripple outward, detached from your own past. Wormholes aren't just shortcuts, they're questions. Questions about identity, memory, and origin. What happens if the person who steps into one isn't the same person who comes out? What if stepping through doesn't just move you, but changes you? And what if someone else is already using one? You wouldn't know. It could be in the sky, in the ocean, in a cave beneath your city. It could be microscopic or cosmic. It could flicker open for a second, let something through, and vanish. Maybe it already did. Maybe it always has. It's the most famous time travel question of all. What happens if you go back in time and kill your grandfather before your parent is born? If you succeed, your parent is never born, which means you are never born, which means you were never there to go back in time and kill him in the first place. So he survives, which means your parent is born, which means you are born, which means you go back and kill him, and so on, forever. This is the grandfather paradox. It's simple, brutal, impossible to solve. It's not about morality. It's not about whether you should kill someone. It's about logic, pure, cold logic. Cause and effect folded in on itself until the system breaks. The paradox doesn't require violence. You could go back and do something small, break a machine, misplace a letter, say the wrong thing at the right time. If the result prevents your time travel from ever happening, the loop collapses. And that's the problem. The moment you alter the past in a way that affects your ability to return to the past, you create an inconsistency, a logical contradiction, one that no timeline can support. So how do we deal with it? There are three main theories. One, you can't change the past. This is the Novikov self-consistency principle. It says the universe won't let you try to kill your grandfather and the gun jams, or you miss. Or he survives somehow no matter what. Everything you do in the past already was part of the past. You just didn't know it. You were always supposed to go back. Your presence changes nothing. It's clean, elegant, and horrifying. Because it means you have no freedom. Time is a locked script, and you are just acting out your lines. 2, changing the past creates a new timeline. This is the multiverse solution. You go back and kill your grandfather successfully, but instead of erasing yourself, you create a branch. A new timeline where your grandfather died and you will never exist, but you continue to exist because you came from a different version of history. It solves the paradox, but it raises questions about identity. Which you are you? Did you just abandon your own world? And how many other timelines have you left behind? 3, you destroy the universe. This one's less popular, but in theory, creating a contradiction might cause a collapse, a glitch in the system, a failure of the timeline to reconcile itself. The equations break, reality crashes. In other words, no more story. No more you. Physicists have spent decades modeling scenarios like this. Some say quantum mechanics, with its uncertainty and branching probabilities, might allow for paradoxes without catastrophe. Others think nature has a built-in defense, some hidden law we don't yet understand, that prevents paradoxical conditions from even starting. But we don't know, because no one has ever gone back. At least not that we remember. And that's what makes the grandfather paradox so terrifying. It's not just a logic puzzle, it's a wall, a boundary. The moment you try to rewrite the past, you hit it, and what's on the other side? Silent. A timeline that can't exist. And maybe shouldn't. Because if cause no longer leads to effect, and effect can precede cause, then all bets are off. You can no longer trust memory, or history, or even thought. And if your actions now can erase your own beginning, what does that say about choice? What does that say about anything? So next time you think about time travel, forget the gadgets and wormholes. Ask a simpler question. If you had the chance to go back and fix something, Would you trust yourself not to destroy everything instead? It was supposed to be just a casual afternoon. Two English women, Charlotte Ann Moberly and Elinor Jourdain, were visiting the gardens of Versailles near Paris. The year was 1901. They were academics, travelers, and neither one particularly given to fantasy. It was August. The sun was out. The air was still. They walked the grounds of the Petit Trianon, a small chateau once favored by Marie Antoinette. But as they wandered the garden paths, something changed. Not suddenly, quietly. Subtly. The atmosphere grew heavy. The light dimmed, not as if clouds had passed, but as if the world had thickened. Colors flattened. The warmth faded. A stillness settled over everything. And then the people. They noticed figures dressed strangely, old-fashioned clothes, tricorn hats, powdered wigs, a man with a scarred face glaring at them beneath a wide-brimmed hat, a woman sitting on the grass sketching in a dress centuries out of date. The entire scene looked staged but without movement, like a painting that had momentarily come alive. The two women grew uneasy. It didn't feel like a performance. It didn't feel like reenactment or costume. It felt wrong, like they had walked into a world that wasn't theirs. They left quickly, but the experience stayed. Months later, they published their account, first anonymously, then under their real names. The book was titled An Adventure. In it, they described what they believed had happened. They had slipped through time. They believed they had walked into Versailles as it was in 1789, just before the French Revolution. They claimed to have seen Marie Antoinette herself, sitting and drawing on the grass near the Temple of Love. Skeptics were quick to dismiss it. Hallucination, misinterpretation, shared delusion, but there were odd details. Descriptions in their story matched locations and objects that weren't public knowledge at the time. A particular bridge, a long-removed doorway, specific costumes, all things confirmed later through historical research. But there were problems too. The story evolved over time. Later editions of their book included new details that hadn't been in the original manuscript. Critics questioned the reliability of memory, especially when filtered through years of contemplation and suggestion. Still, the case lingered. Because it wasn't just what they saw, it was how it felt. They described the shift in atmosphere, the way the air changed, the emotional weight, the silence. Many people who claim to have experienced time slips describe similar sensations, a sudden stillness, a pressure in the chest, a sense that reality has turned inward. And the Versailles incident isn't unique. Throughout history, scattered reports exist of people briefly finding themselves in places that don't belong to their time. A man walking through Liverpool in the 1990s who claims to have entered a store that hadn't existed since 1953. A driver in Spain who takes a wrong turn and finds himself on a road that hasn't been paved yet. A couple in the French countryside who book a hotel that vanishes the next day. All unproven, all dismissed, but hard to forget. What if time isn't a river? What if it's a landscape, layered like sediment, thin in places, thick in others? What if just occasionally those layers shift? You take a step and the ground beneath you is suddenly earlier. Not imagined, not remembered, experienced. Like Versailles in 1789, blooming into view for just a moment. We have no explanation for time slips, no mechanism, no machine, no field theory, and yet the stories continue. They don't follow the rules of physics, but they follow the rules of dreams, of memory, of déjà vu. And that's the disturbing part. Because if time can slip without technology, without intent, what else can it do? Can you get stuck? Can you leave something behind? And if the past can briefly reappear, what happens when the future does? In most science fiction stories, faster-than-light travel is just a button away. A warp drive, a jump gate, a glowing portal. But in real physics, the speed of light is a hard limit. Nothing with mass can reach it. Nothing with mass can cross it. That's what makes light special. It's the fastest thing in the universe, at least as far as we know. But what if there's something faster? Enter the tachyon, a hypothetical particle that, if it exists, would always travel faster than light. Not sometimes, not when boosted, always. The idea came from attempts to understand quantum field theory. Mathematicians noticed that some solutions to their equations allowed for particles with imaginary mass. Not imaginary like pretend, but imaginary in the mathematical sense. involving the square root of -1, the kind of number that suggests something fundamental is out of sync. And if such a particle existed, it couldn't slow down to light speed. It could never go slower. Its natural state would be beyond the light barrier, which means it could reach the future before the present is over. Or it could arrive before it was sent. In theory, if you could use tachyons to send a message, that message could reach its destination before it was transmitted. From the perspective of the sender, you hit send. From the receiver's perspective, the message was already there, waiting. This isn't time travel in the traditional sense, no portals, no ships, but it's a violation of causality. The effect precedes the cause, information arrives before it exists, the timeline unravels. And that's where the trouble starts. Because if you can send a message into your own past, you can change your decision before you make it. You can create paradoxes. You can collapse logical systems. You can build a loop of intention that feeds on itself. You don't need to kill your grandfather. You just need to warn yourself not to send the message. And if you listen, you never send it. So how did you get it? Tachyons haven't been detected. There's no proof they exist, but they haven't been ruled out either. They remain a mathematical possibility, an edge case, a ghost in the equations. Many physicists believe they're unphysical, that their presence in a model just means the model is unstable. But some disagree. Some believe tachyons are real and hidden, that they exist in a realm we can't yet probe, that they interact weakly or not at all with ordinary matter, that they pass through us constantly, too fast to notice, leaving no trace. And some believe they don't just carry information. They are information. Encoded, fractured, dispersed across space-time, echoes of future events bleeding backward, precognitive flashes, intuition, dreams that feel like warnings, words on the tip of your tongue you never meant to say. What if tachyons aren't science fiction? What if they're how time communicates with itself? A closed loop of messages that fold across the timeline, shaping it quietly. A nudge here, a choice there. Not enough to break causality, but enough to bend it. And what if one already reached you? Not in a machine, not in a lab, but in a thought, a feeling, a moment of hesitation right before something changed forever. Imagine the early universe, just moments after the Big Bang, hot, dense, chaotic, a sea of particles, forces, and energy fields still sorting themselves out. As the universe cooled, these fields began to settle, like ice forming on a lake. But what if they didn't settle perfectly? What if, in that frozen structure of space-time, some cracks remained? Enter cosmic strings, thin, ultra-dense filaments of energy stretching across the universe. Hypothetical relics of the universe's birth, not strings in the ordinary sense, but rips in space-time, thinner than an atom, but possibly as long as galaxies. They're not made of matter, they're made of tension. Imagine a fault line, not in rock, but in the fabric of reality itself, a line where the universe didn't quite match up. And here's where it gets strange. Because cosmic strings don't just bend space. They bend time. According to general relativity, a moving cosmic string, especially two strings passing close to each other, could distort spacetime in such a way that it creates a loop, a closed, time-like curve. That means a path through space and time that returns to its starting point, a loop not just in location, but in causality. In theory, if you could fly a spaceship around two moving cosmic strings in just the right way, you could emerge before you left. You'd be back in your own past. No wormhole, no machine, just geometry, just physics. But there are problems. First, we've never found a cosmic string. Second, you'd need to travel at near the speed of light, with perfect precision. Third, the energy involved would be catastrophic. And yet the math checks out. The idea isn't from science fiction. It comes from serious physicists, people like J. Richard Gott, who in 1991 proposed a model where time travel could be possible using just two moving cosmic strings and Einstein's equations. It's elegant, cold, precise. But what does it mean? What does it mean that the shape of the universe itself, its folds, twists, and scars, might allow for travel through time? It suggests that time isn't just a direction, it's a terrain, a landscape you can navigate if you know the contours, a place with valleys and shortcuts, bottlenecks and loops, and some of those loops might still be out there, untouched, unnoticed, untriggered. Waiting. Waiting for a particle to pass through. Waiting for a traveler. Waiting for an accident. And what if one is near us? What if a cosmic string drifted silently through our solar system? We wouldn't see it, we wouldn't hear it, it wouldn't block light, it might distort it slightly like a ripple in glass, a lensing effect, a shimmer. You could walk through it, or fall through it, and wake up yesterday, or 1,000 years from now. Cosmic strings don't ask your permission. They don't care what you want to change. They're not portals or prophecies. They're just the broken edges of a universe that cooled too fast and left behind threads of impossible potential. And somewhere, one of them might be vibrating still. A line across time. Dot, waiting to be touched. You're walking through a park, the air is still. A butterfly flutters past, landing on a leaf. It lifts off again, just a tiny shift of air, harmless, forgettable. But 1,000 miles away, that motion adds a ripple to the breeze. That ripple pushes a warm front into a cold one. Clouds begin to form, pressure builds. Days later, a storm hits a city. And in that storm, someone misses a train. And because they missed it, they never meet the person sitting in seat 4B. Which means a child is never born. Which means a different leader rises decades later. Which means the laws change, a war begins, a technology is delayed, a cure is missed, a catastrophe unfolds. All from a butterfly's wings. This is the butterfly effect, the idea that small causes can have vast, unpredictable consequences. It's not about time travel in the traditional sense. It's not about machines or portals. It's about sensitivity, about how every moment contains the seeds of transformation. The concept comes from chaos theory, a field of mathematics that deals with systems so complex, so interconnected, that tiny variations in initial conditions lead to drastically different outcomes. Weather is a classic example, so are ecosystems, stock markets, human lives. In time travel, the butterfly effect is its nightmare. Because if you go back in time, just for a minute, and step on the wrong blade of grass, you might rewrite everything. Say you visit the year 1850, you smile at a stranger, he takes a different road home, he gets caught in the rain, he meets someone else, marries her, their children grow up in a different town, one of them becomes a teacher instead of a doctor, that teacher inspires someone who builds a new kind of engine, that engine powers an invention that changes how cities grow. And now you're standing in a future you don't recognize. Not because you meant to change anything, but because you were there. The butterfly effect makes time travel dangerous, not just for grand missions, killing dictators, stopping disasters, but for the very act of arrival. You can't help but change things, by breathing, by walking, by looking. You're not a visitor. You're a variable. Some fiction tries to get around this with fixed timelines, worlds where history corrects itself, where outcomes bend back toward the original shape, but chaos theory suggests the opposite, that the farther back you go, the more powerful your smallest choices become. Because early in any system, the possibilities are wide open, paths haven't forked yet, the map hasn't narrowed, and a tiny nudge then becomes an avalanche later. This is why the butterfly effect haunts time travelers. Because you can't predict it, you can't trace it, and you can't undo it. Even coming back to your own time, you'd never know what you changed. A word in the wrong ear, a look that lingered too long, a note misplaced, a door opened that was meant to stay closed. And maybe you're living in a world that someone already changed. Maybe the life you know, the politics, the people, the climate, the art is already version 5, or 50, or 5,000. You wouldn't know, because a different butterfly flapped its wings long ago. And here you are, thinking it was all inevitable. It started with a question that sounded like a joke. What if a material could move in time without using energy? Not metaphorically, not philosophically, physically. In 2012, Nobel laureate Frank Wilczek proposed something strange, the idea of a new phase of matter, something that doesn't just repeat in space, like a crystal, but in time. A structure that oscillates, flips, or cycles forever without input, without energy. A motion that never ends but never starts, like a clock that ticks without a battery. He called it a time crystal. At first, the physics world laughed it off. Perpetual motion, violating thermodynamics, it couldn't work. But then in 2016, a team at the University of Maryland built one. And then another team at Google built one using quantum processors. And suddenly, time crystals weren't science fiction anymore. They were real. To understand them, you have to forget what you know about movement. In our world, when something moves, it consumes energy. Your heartbeat, a pendulum, a planet, everything that ticks or turns must be powered by something, and eventually, it runs out. But in the quantum world, things get weird. You can create systems that are isolated, where particles interact in just the right way to avoid heating up, avoid randomness, and avoid decay. In these systems, time crystals can form. They don't move like normal objects. They oscillate between states, back and forth, predictably, repeating in time the way atoms in a regular crystal repeat in space. And once they start, they never stop, unless you destroy the system. That's what makes them feel like time travel. Because they don't age, they don't slow. They're eternally cycling, trapped in a rhythm that defies our understanding of entropy, the rule that says everything eventually runs down. Time crystals aren't breaking the laws of physics. They're dancing in the spaces between them. And here's where it gets even more strange. Some researchers now believe that time crystals might be useful for quantum computing, because their stability in time could act as a kind of clock inside systems that usually fall apart under observation. Others speculate more wildly. What if time crystals exist naturally? What if they formed in the early universe? What if there are places hidden, rare, protected, where time loops gently forever? No decay, no forward movement, just oscillation, a heartbeat frozen in a moment, not dead, not alive, just repeating. And what if consciousness could interact with that? What if memory is not linear, but cyclical? What if déjà vu, premonition, or certain altered states of perception are moments when your brain, briefly, touches something that doesn't move forward in time like you do? A time crystal isn't a machine. It's not a doorway. It's a pattern, a rhythm. Something that pulses without cause, without end, without meaning. But if time can crystallize, if it can freeze into a structure, then maybe time isn't what we thought it was. Maybe it's not a flow. Maybe it's a fabric. And maybe, just maybe, there are places in that fabric where the threads fold in on themselves and shimmer, trapped forever in their own music. Most people have never heard of it. There are no official documents, no congressional records, no NASA briefings, just the word of one man, Andrew Basiago. According to him, in the late 1960s and early 1970s, the U.S. government ran a secret time travel program called Project Pegasus. And he wasn't just a witness, he was one of its child participants. He claims he was teleported across the United States, stepped into parallel timelines, and even traveled to the past and future, all as part of a DARPA-led experiment in temporal mechanics. Sounds ridiculous, but the details are what make people listen. According to Basiago, the core technology was based on designs found in the papers of Nikola Tesla, specifically documents recovered after Tesla's death in 1943, when his hotel room was seized by the U.S. Office of Alien Property. Within them, he says, were blueprints for a teleportation chamber powered by radiant energy and magnetic fields. The chamber was allegedly constructed in New Jersey and later used to train a group of children to travel through time and space. Children, he says, were chosen because their minds were more adaptable to the psychological strain and their bodies more resilient to temporal displacement. Basiago described walking through a curtain of energy, like static air, feeling a mild snap, and suddenly finding himself in a different place, sometimes a different year. In one case, he claims to have traveled back to Gettysburg just days before Abraham Lincoln delivered the Gettysburg Address. Dressed in period clothes, he wandered the crowd as an observer. Years later, he pointed to a real photograph, one published long before his story came out, and claimed he was in it. In another story, he says he visited the year 2045, a sterile, automated future, and brought back data stored on a tiny crystal device. He also mentions trips to Mars, contact with extraterrestrial beings, and meetings with U.S. presidents before they were elected, including one, Barack Obama. If it all sounds too far-fetched to believe, you're not alone. Mainstream scientists dismiss the claims, journalists ignore them, there's no physical evidence, no proof, just testimony. But the structure of the story, the way it's told, the consistency across interviews and years, it leaves a strange residue. It doesn't feel like fiction. It feels like something else. What if some version of Project Pegasus really existed? Maybe it wasn't as dramatic, maybe it wasn't successful, maybe it never got past the first phase. But think about the time, post-World War II, deep into the Cold War, during a period when governments were pouring money into black-budget projects with zero public oversight. We were already experimenting with nuclear weapons, psychotropics, mind control, radiation, and stealth aircraft. Is it so hard to imagine that someone tried to push time? Not for travel, for intelligence. Imagine if you could look 1 week into the future, just long enough to see market moves, political events, terrorist attacks, scientific breakthroughs. You wouldn't need to go far. Just far enough. Project Pegasus, if it existed, may not have been about adventure or exploration. It may have been about control, prediction, advantage. And if it failed, all the better to bury it. So what do we do with stories like Basiegos? Dismiss them, or log them away as artifacts, glimpses of experiments that may have been tried, tested, and forgotten. Because even if he's wrong, what if he's not entirely wrong? What if the truth isn't that he saw too much, but that he remembered something he wasn't supposed to? It began with a simple question: if you're riding on a beam of light, what does the world look like? That's what a young Albert Einstein asked himself as a teenager. Years later, that question would lead to one of the most revolutionary ideas in physics, the theory of special relativity. It didn't require any advanced math, no laboratories, just a notepad, a mind, and a willingness to question everything. The result: a complete rewrite of how we understand space, time, and how they relate. In the world before Einstein, time was assumed to be absolute. Events either happened before or after one another, everywhere, for everyone. A second was a second, a meter was a meter, space was space, time was time. But Einstein proposed something radical. The speed of light is constant, for everyone, everywhere, no matter how fast they're moving. And if that's true, then time cannot be. Think about two people, one standing still, one flying in a spaceship at nearly the speed of light. They each shine a flashlight. Einstein's equations say both beams of light travel at the same speed, exactly the speed of light for both observers. But how can that be if one person is moving and the other is? The answer: their experiences of time and space must stretch and contract to balance out. Time slows down for the traveler. Distances shrink. Simultaneity, what now means, falls apart. Two events that happen at the same time for one observer may happen at different times for another. There's no universal now. Every person carries their own clock, their own slice of space, their own direction through time. This sounds abstract, but it's not. It's real. We measure it. Astronauts aboard the International Space Station age slightly slower than people on Earth due to time dilation. GPS satellites must adjust their onboard clocks for both gravitational and velocity-related time shifts. If they didn't, your location would be off by miles. And in that adjustment, those nanoseconds corrected every day, you can feel the edge of time's fabric shifting. Einstein showed that time isn't a background, it's not a stage where things happen, it's part of the show. It bends, it slows, it changes based on where you are and how fast you're moving. And here's where it gets strange. If you move fast enough, close to the speed of light, you can make time on Earth pass faster. You could travel for what feels like a few years to you and come back to find decades have passed. Everyone you knew might be older or gone, the world would have changed, and you wouldn't have aged the same way. This isn't hypothetical. It's the foundation of the twin paradox, something we've already explored. But it all begins with special relativity, Einstein's first great step. A world where space and time aren't fixed, but fluid. Where your motion doesn't just move you through the world, but bends your experience of reality itself. So next time you look at a clock, ask yourself, whose time is it really? Yours? Mine? Or is every second just a local illusion, stitched together from motion and memory? Right now above your head, about 400 kilometers up, there are people orbiting Earth at 28,000 kilometers per hour. They live on the International Space Station, ISS. They float, they sleep strapped into bags, they sip water in weightless globs, and without realizing it, they are time travelers. Not in science fiction, in science fact. Because up there, time ticks differently. Thanks to Einstein's relativity, we know that both speed and gravity affect how fast time passes. The faster you move, the slower your clock ticks, and the farther you are from a massive object like Earth, the faster your time moves relative to someone closer. On the ISS, both effects are in play. Astronauts move incredibly fast, so their time slows down. But they're also farther from Earth's surface, so their time speeds up. It's a tug of war. But speed wins. The result, astronauts aboard the ISS age more slowly than we do. Not by much. If you spent 6 months in orbit, you'd return to Earth a few milliseconds younger than everyone else. But it's real. We've measured it. Atomic clocks on Earth and clocks on the ISS don't stay perfectly in sync. Even clocks flown on high-speed jets or moved between floors of a building tick at slightly different rates. Your head actually ages faster than your feet because it's farther from the center of Earth's gravity. We live in a world where time is flexible, even if we can't feel it. And here's where it gets interesting. Time dilation isn't just trivia, it's part of everyday technology. GPS satellites orbit Earth at high speed and at high altitude. If we ignored relativity, GPS signals would drift out of sync, causing errors of kilometers per day. Your map app would think you were in the next town, or in the ocean, or moving when you're standing still. To fix it, engineers built Einstein's equations into the system. Every satellite's onboard clock is adjusted to compensate for relativistic effects. They run slightly slower than clocks on the ground, and the difference is calculated constantly to keep the network aligned. Which means every time you get directions, or find a restaurant, or track a delivery, you're using time travel math. The ISS is a lab, a symbol, a floating outpost, but it's also proof that the flow of time is not constant. Imagine if the station orbited faster, or farther. Imagine future missions to Mars or deep space. For astronauts on long-duration journeys, time dilation won't just be milliseconds, it could be minutes, hours, days. A crew returning from a 10-year voyage might come home to find that 20 years passed on Earth. And the more we push into the cosmos, the more time becomes a resource, something to measure, to manage, to anticipate. Time isn't just what you count, it's what you carry. So the next time you look up at the night sky, remember, someone up there is living in your future by a fraction of a second. Their heartbeat is slightly delayed. Their time is not your time. And one day when we go farther, faster, and longer, that delay might be years, or centuries, or something we no longer have a word for. It's one of the earliest viral mysteries of the internet age. In 2010, an Irish filmmaker named George Clark uploaded a clip to YouTube titled, "Time Traveler Caught in 1928 Charlie Chaplin Film." It wasn't clickbait, it wasn't edited. It was a piece of raw footage, a behind-the-scenes segment from the premiere of Charlie Chaplin's film The Circus, shot outside Grauman's Chinese Theater in Hollywood. The footage was from 1928, black and white, grainy, silent. But then, at about 1 minute and 10 seconds in, you see her. A woman walking across the frame. She's dressed in black, wearing a large dark coat. A hat shadows her face. and she's holding something to her ear. She's talking. Mouth moving, gestures clear. One hand holding something to the side of her head, just like someone on a phone. Except it's 1928. There were no mobile phones. No wireless handsets. Not even props that resembled them in common use. So what is she doing? George Clark believed it was a moment out of time, a glitch, a traveler, someone carrying a device she shouldn't have had, casually strolling past Charlie Chaplin's camera crew mid-conversation as if she belonged there. The video sparked massive speculation. Was it a cell phone? Some argued yes, pointing to her posture, the natural way she moves, the way she seems engaged with someone on the other end. But there's a problem. There were no cell towers in 1928, no infrastructure. Even if she had a device, there'd be no one to call. Others claimed it was a hearing aid, a Siemens model from the 1920s that required holding a rectangular amplifier to the ear, but side-by-side comparisons didn't quite match. The shape was wrong, the behavior didn't fit. And some said it was nothing at all, just a moment taken out of context, misunderstood by modern eyes, a trick of posture, a coincidence. But the feelings stuck. Because the video was real, the footage was authentic. The people were unaware of cameras in the same way we're caught on Street View today. There were no reenactments, no filters, just a woman walking, doing something no one could quite explain. What makes the clip so eerie is how natural it feels. She isn't glowing, she isn't looking around confused. She looks comfortable, like someone who's used to being there, used to time moving differently. And that's what makes time travel terrifying. Not the machines, not the portals, but the possibility that it already happened and we just missed it. Because a true time traveler wouldn't draw attention. They wouldn't interfere. They'd blend in. They'd walk past a premiere, glance at the camera, and vanish into history. And maybe what we're seeing isn't a mistake. Maybe it's a message. Not from her, but from us. A reminder that sometimes the most inexplicable clues are already in the archive, already in the footage, already in the past, waiting to be rewatched. And maybe the real question is, did she have a phone? But how did we recognize it? How did our brains, without hesitation, say, she's on a call? Unless we've seen her before. Imagine a wall on one side, a particle, on the other, emptiness. In classical physics, that particle doesn't stand a chance. If it doesn't have enough energy to climb the wall, it stops, stays, bounces off, simple. But in the quantum world, things don't stay where they're supposed to. Sometimes the particle just appears on the other side. No climbing, no breaking through, it simply moves, as if the wall wasn't there at all. This is called quantum tunneling. It's not magic, it's one of the most well-documented effects in quantum mechanics. It happens in radioactive decay, in electronic circuits, even in the sun. Without tunneling, fusion in stars wouldn't be possible. But how does it work? At the quantum level, particles aren't like marbles. They're probabilities, smears of possibility, a cloud of where they might be. That cloud doesn't stop at the wall, it bleeds into the other side. And if part of that probability exists beyond the barrier, there's a chance, however small, that the particle will show up there. It's not going through. It's already being there. But now imagine something stranger. Imagine the moment the particle appears on the far side, influences whether it ever existed on the near side. Welcome to retro-causality, the idea that the future can affect the past. Some interpretations of quantum mechanics suggest that outcomes in the future can reach back and shape the conditions that led to them. That measurement isn't just recording reality, but selecting it, even retroactively. Take the delayed choice quantum eraser experiment, which we'll explore later. It shows that whether a particle behaves like a wave or a particle can depend on a decision made after the event. Think about that. The particle behaves now based on something that hasn't happened yet. As if time is being rewritten in both directions. Some physicists dismiss this as a quirk of interpretation, saying it's just how the math works out. But others argue that it suggests something deeper, that causality is not fixed, and that the future can, under certain conditions, determine the past. Not metaphorically, literally. And here's where it gets disturbing. If the future can influence the past, then where does choice fit? If your decision at time t plus 1 shapes what happened at time t, what you do is already encoded before you do it. Is that destiny? Or is time a loop, constantly feeding itself? Quantum tunneling is harmless when it's just particles. But what about people? What if your memory is like a wall, and ideas tunnel into your mind from a future that hasn't happened yet? What if intuition, coincidence, or sudden understanding is just a form of retrocausality? What if your future self is sending instructions back? Not in language, not in words, but in nudges. In glances. In dreams. In mistakes. Maybe you're already on the other side of the wall. Maybe you never had to climb it. Maybe the reason you made it this far is because something ahead already decided you would. It starts with a beam of light. You shine it at a screen with 2 slits. Behind the slits, another screen waits to catch the light. Fire the photons one at a time and something strange happens. They form an interference pattern, not 2 lines like particles should, but many lines like waves interfering with themselves. That means each photon, each individual piece of light, somehow went through both slits at the same time. But if you try to measure which slit it went through, the interference pattern disappears. It behaves like a particle again, like it only chose one path. The act of measuring changes the outcome. This is the famous double-slit experiment, and it already makes reality feel like a trick mirror. But in 1999, physicists pushed it further with the delayed choice quantum eraser experiment. And that's when things got deeply weird. Here's what they did. They fired photons at the double slits as before, but this time they entangled each photon with a partner. Think of it like creating twins. Whatever happens to one affects the other, instantly, no matter how far apart they are. The original photon goes toward the screen. The entangled twin goes the other way, toward a detector setup that might tell you which slit the original photon went through, or might not, depending on how the detectors are configured. Here's the twist. The choice to preserve or erase the which path information about the photon is made after the original photon has already hit the screen. So you're deciding in the present whether the photon in the past behaved like a wave or a particle. And yet the results still match. If the which path information is preserved, the interference disappears. If it's erased, the interference returns. As if the photon knew in advance what you were going to decide. As if its past behavior depended on a future event. Not just predicted it. Depended on it. You can't use this to send messages back in time. The pattern only makes sense after comparing many results, but the logic is still shocking, because it suggests that causality is not one way. The photon's path through time is incomplete until all parts of the experiment are observed, even those in the future. So what does that mean? Is the universe waiting for us to look before it finalizes its past? Is every moment not fully real until someone remembers it? And if your future actions can reach into the past of a particle, can they reach into your own? Can your future self reach back? Not with a machine, but with a choice. A decision you haven't made yet that explains a coincidence from years ago. A pattern in your life that only now starts to make sense. A moment you can't explain until one day you do something and suddenly it fits. The delayed choice quantum eraser doesn't tell us that time is fake. It tells us that time is incomplete. That reality is provisional, mutable, collapsing only when it must. And until then, the past is still listening. At the border of France and Switzerland, buried deep beneath the countryside, a ring of machinery stretches 27 kilometers underground. It's called the Large Hadron Collider, or LHC, the most powerful particle accelerator ever built. Operated by CERN, it was designed to answer the deepest questions in physics. What is matter made of? What force holds the universe together? How did time begin? But not everyone is convinced that's all it does. Some believe the LHC is pushing on time itself. The idea doesn't come from conspiracy theories, it comes from math. When the LHC smashes particles together at nearly the speed of light, it recreates conditions that existed just fractions of a second after the Big Bang. Temperatures soar, fields twist, energy bends space. In those collisions, particles flicker in and out of existence, some so unstable they exist for less than a billionth of a second. Yet in that blink, something happens that defies ordinary thinking. Causality begins to wobble. In 2008, just before the LHC was first powered on, a handful of physicists, serious ones, from respected institutions, proposed a wild idea. What if the universe doesn't want the LHC to succeed? What if the machine, by reaching certain energy levels, creates a ripple backwards in time that stops it? They were joking, kind of. But the idea came with equations. The theory went like this: if the LHC were to create certain exotic particles, like the Higgs boson, in a specific configuration, it might create a feedback loop that extends backward in time. That loop would influence past events in subtle ways to prevent the LHC from reaching that moment. Accidents, budget cuts, unexplained delays, even sabotage. It would be like time correcting itself. Of course, this sounds ridiculous until you realize something odd actually happened. The LHC's first major run was delayed. On September 19, 2008, just 9 days after the grand activation, a helium leak triggered a catastrophic failure. The project was shut down for more than a year. A few months later, a maintenance error caused by a technician became international news. The twist: that technician claimed to have been receiving instructions from beyond, something he couldn't explain. Coincidence? Probably. But the idea never quite died. Because what the LHC is actually doing still isn't fully understood. When the Higgs boson was confirmed in 2012, the world celebrated. It was called the God particle, not because of religion, but because it was the final piece in the standard model of physics. The Higgs field gives mass to other particles. Without it, matter couldn't exist. But Higgs particles are unstable. They decay in strange, unpredictable ways. Some theorists believe that in extreme cases, Higgs-related events could trigger vacuum decay, a reshaping of the very structure of the universe. Or more interestingly, that their behavior might not obey standard temporal rules, that Higgs fields, when disturbed at high enough energies, could ripple both forward and backward in time. This is more than theoretical musing. Quantum field equations don't explicitly forbid backward time evolution. They allow solutions that include closed Timelike curves, entangled retrocausality, and non-local interactions, where the present outcome seems to affect the past setup. And in the LHC, all of those are being pushed. Minute by minute, collision by collision. Billions of particles racing into one another, forming unstable microstructures, many of which exist in overlapping time frames. Some calculations even show that under certain spin and energy values, a particle's worldline, its path through spacetime, can fold in on itself. Which means miniature time loops, tiny, closed circuits of causality. They don't last long, but maybe they don't have to. In these fleeting moments, time might not be linear. Information might move both ways. A particle might decay before it's born. A result might arrive before the experiment begins. The LHC's own sensors have occasionally picked up unexplained anomalies, data spikes, ghost signals, missing mass. Nothing conclusive, but nothing easily explained either. And then there's the matter of black holes. Some physicists feared the LHC might accidentally create micro-black holes, tiny, dense knots of spacetime so small they'd vanish instantly. CERN insists that's impossible, but the equations don't rule it out. And if even one such singularity formed for a trillionth of a second, it might not destroy the world. It might just twist time in a way we don't yet understand. So what if the LHC isn't just a machine for probing matter? What if it's a mirror? A place where the future sends back messages, not in language, not in symbols, but in probabilities, in quantum nudges, in failure, in coincidence, in strange dreams of engineers who don't know why they hesitate. And what if one day we trigger something that doesn't just go backward, but wise, a ripple that folds the timeline, a particle that remembers its future, a world line that writes its own past? The Large Hadron Collider may not be a time machine in the traditional sense, but it may be something more dangerous. A place where time forgets which way it's supposed to go, and keeps trying until we notice. Close your eyes. Now imagine that in the endless void of space, a place with no stars, no planets, no galaxies, something flickers into existence. Not a world, not a creature, just a brain. Fully formed, conscious, alone. It lasts for a moment, long enough to think a thought. Maybe it thinks it's you. Maybe it remembers a life it never lived. It wonders where it is. It screams inside itself, and then gone. This is the idea of a Boltzmann brain. And it might be more likely than your entire life. The concept comes from 19th century physicist Ludwig Boltzmann, who tried to explain entropy, the measure of disorder in the universe. According to thermodynamics, the universe is always moving from order to chaos. Ice melts, buildings crumble, stars burn out. The general direction of time, the arrow of time, is set by this increase in entropy. But Boltzmann proposed something counterintuitive. He suggested that, over a long enough period, random fluctuations in the fabric of reality could spontaneously create pockets of order. A cold patch in a hot gas, a molecule that drifts back into place, even a full solar system, if you wait long enough. Given infinite time, anything can happen. And the universe, as far as we can tell, is very old. Possibly infinite. Certainly vast. Now follow that logic. If the universe can randomly produce ordered systems, what's more likely? That it assembles an entire universe like ours, with billions of galaxies, stars, planets, life, evolution, intelligence, culture. Or that it assembles one brain, floating in the void with false memories of all of it. Statistically, the brain is far more likely. It's smaller, simpler, requires fewer improbabilities. And that means, if we take entropy seriously, there's a disturbing possibility. You might be one. Right now, everything you remember, your childhood, your family, the taste of coffee, the sound of your own voice, might not have happened. It might be part of a thermal fluctuation that briefly, randomly, created a functioning consciousness with implanted memories, poised to fade back into chaos. From your perspective, everything feels continuous. But that's the trick. A Boltzmann brain would feel real. Because it has to. If it didn't, it wouldn't be a consciousness. It wouldn't experience the doubt. So the very fact that you're questioning it makes it more plausible. This isn't just philosophical paranoia. It's a real problem in cosmology. If certain models of the universe suggest that random fluctuations are the main way conscious observers arise, then most observers shouldn't live in ordered worlds. They should be isolated minds in chaotic voids. And that creates a paradox. Because we see stars, we see order. We measure the age of galaxies and the structure of the cosmos. That suggests we're not Boltzmann brains. But we can't be sure, because even that evidence could be part of the illusion. Maybe you're in a white room. Maybe everything around you is noise, dressed as form. Maybe the next time you blink, you'll never wake up. Not because you die, but because your improbability expires. The fluctuation ends. The universe resumes its disorder. And your moment of you collapses into nothing. So why does this matter? Because it asks something terrifying. What's more fundamental, reality or the experience of it? Would you rather be real in a cold, dead world? Or be fake in a dream that feels warm? And if you can't tell the difference, does it even matter? You're sitting in a chair wearing a headset. At first, it's just a blank room, digital, geometric, harmless. Then the environment shifts, the floor becomes stone, the air flickers with torchlight. You hear voices in Latin, you're standing in a Roman bathhouse. You reach out to touch the marble pillar beside you, and though your hand meets nothing, your brain swears it's there. You walk. Soldiers pass. A senator argues nearby. The sunlight falls through a painted dome, and as you tilt your head up, your body forgets where you really are. This isn't time travel, but your brain doesn't care. Welcome to the world of simulated time travel, not in the future, not theoretical, but happening right now. In labs, in research centers, in therapy sessions, in museums, in prisons, in classrooms, in military programs, everywhere reality starts to dissolve into experience. And it's changing the way we think about memory, identity, and time itself. The premise is simple. Your brain constructs its sense of now based on sensory input. What you see, hear, feel, these signals tell your brain what's happening, but that input is flexible. It can be hacked. Virtual reality doesn't have to be realistic. It just has to be consistent. And when it is, your brain surrenders. In 2014, researchers at the University of Barcelona ran an experiment. Participants were placed in VR and given a new body, a child's body or a different race or a different gender. Within minutes, the participants began to internalize the new identity. They moved differently, felt differently. Some even reported false memories, as if they'd lived experiences in that virtual body they never actually had. Now stretch that over time. What if you enter VR and it's not just another body, but another era? You're born there, raised there. The sky, the language, the customs, the gravity of decisions, it all matches. You stay for hours, days, weeks. In some cases, your body outside is cared for, fed, maintained. Inside, you live. And when you exit, something's wrong. The world feels off. The people seem shallow. The sounds too quiet. You miss a language you never spoke. You grieve people who never existed. You remember decades you never lived. Your brain is not broken. It's just been convinced. Simulated time travel isn't about sci-fi fantasies. It's about what happens when the illusion of history becomes indistinguishable from lived experience. And it goes deeper. Neuroscientists have found that reconstructing the past in VR helps memory patients recover long-lost thoughts. War veterans re-enter scenes from their own history to rewrite trauma. Prisoners revisit crimes. Therapists walk addicts through their own childhood homes. Sometimes people come out changed. They say, I saw myself at age 9. I remembered what I wanted. They say, I watched my parents fight again, and this time I walked away. They say, I went back and apologized. I know it wasn't real, but it was enough. What does that mean? That we don't need real-time travel to change the past. We just need a simulation good enough to fool the brain into feeling closure. And now imagine the next step. Neural implants, memory editing, dream VR that you can't distinguish from waking. Artificial life paths where you grow old, raise children, love, lose, and die, only to wake up young again in the real world. 10 minutes passed, you lived 70 years. Would you go back in? Would you choose a better past? A different youth? Would you try again? Simulated time travel forces a terrifying question. If the experience is real to you, does it matter whether it's real at all? Maybe the future of time travel won't require machines that bend physics. Maybe it'll just require code. And your consent. You go to sleep on Sunday night knowing you're part of an experiment. Here's how it works. You'll be put to sleep on Sunday. On Monday, a coin will be flipped. If it lands heads, you'll be woken up on Monday, asked a question, then put back to sleep. If it lands tails, you'll be woken up on Monday, asked the same question, put back to sleep, and then woken up again on Tuesday and asked the question again. Each time you're woken up, your memory of previous awakenings is erased. You don't know what day it is. You don't know how many times you've been woken. You don't even know what the coin landed on. Then it happens. You open your eyes, the room is quiet, the question is asked. What is the probability that the coin landed heads? What do you say? Your instincts might tell you it's 50%. The coin is fair, right? It's either heads or tails, but you've just been woken up, and if it was tails, you'll be woken up twice. That means there are 2 chances to experience being awake if the coin landed tails, and only 1 chance if it landed heads. So statistically, you're more likely to be in a tails awakening. Some philosophers say the correct answer is 1-3. Others argue it's still 1-2. And some say both answers are right, depending on how you define the question. This is the Sleeping Beauty paradox. It sounds like a brain teaser, but beneath it lies something deeper. A trap hidden inside self-awareness. Because what this paradox really asks is, what do you believe when you can't trust your memory? What does probability mean when you are part of the experiment? When you become uncertain not just of the world, but of your own identity in it. This isn't just hypothetical. We experience fragments of this paradox all the time. When you wake up and don't know what day it is. When you dream and forget and dream again. When you feel like you've lived a moment before. When memory itself becomes unreliable. And it goes even further. Imagine a future where you can be put into suspended animation, where you can be woken up in different scenarios, where your memories are altered or paused, where you, like Sleeping Beauty, live in controlled episodes with incomplete awareness. What is you in that world? Is it the version that woke on Monday? Or the one that woke again on Tuesday? Are they the same person? They fail the same. They answer the same. They don't remember the other. And here's the terrifying implication. What if you are a sleeping beauty right now? What if this moment, this day, is just one awakening in a sequence of forgotten loops? What if your past decisions were reset, your memories rearranged? What if reality is asking you a question over and over again, and you never realize it's the second time? Or the third? Or the thousandth? You don't remember yesterday the way it happened. You only remember the version of it that came with this awakening. So when someone asks, "What do you know?" the answer becomes slippery. You know what you're told. You know what you recall. But what if that recall is part of the experiment? And what if the real question isn't about coins or days, but this? How many times have you already opened your eyes and thought it was the first time? You walk into a room, a friend is sitting at the table, you sit, talk, laugh, leave. From your perspective, that event is over, gone, a memory. But what if it is? What if that moment is still there, still real, existing just as much as this one, just as much as tomorrow? This is the idea behind the block universe theory, also known as eternalism. It suggests that the past, present, and future all exist simultaneously. That time is not flowing like a river, but laid out like a landscape. And you, the observer, are simply moving through it, frame by frame, like a needle running across a vinyl record. It's a concept rooted in the equations of physics, particularly Einstein's theory of relativity. In special relativity, different observers moving at different speeds experience different presents. Two events that are simultaneous for one observer may not be simultaneous for another. That means the idea of a universal now doesn't exist. Instead, every observer has their own version of now, depending on how they move through space. If there's no single present moment, then all moments must be equally real. Like frames of film in a reel, the entire timeline, past, present, and future, already exists. You just haven't gotten to the later frames yet. To you, the future is unknown. To the universe, it's already there. Imagine your entire life laid out like a four-dimensional sculpture. Every thought, every breath, every choice, fixed in space-time. You're not traveling through time. You are time. A sequence, a whole, a complete object stretched from birth to death. This isn't just abstract theory, it has consequences. If the block universe is true, then free will is an illusion. Your decisions feel spontaneous, your life feels open. But from the outside, viewed as a block, it's all already written. The choice you think you're about to make, you've already made it. And the reason you think you're making it now is because this is the frame your consciousness currently occupies. You're just experiencing time from the inside. Some physicists are comfortable with this. After all, the laws of physics don't distinguish between past and future. The equations work the same in both directions. The arrow of time, the one that moves forward, is a product of entropy, not the fundamental structure of reality. But for most people, this idea feels wrong. It feels cold, deterministic, lifeless. How can the universe be already finished if we feel like we're still writing it? But here's the twist. Just because the block is fixed doesn't mean it's meaningless. Your experiences still matter inside the frame. Your joys, your regrets, your loves, they are all etched into the structure of time. They don't vanish. They don't happen and fade. They exist. Forever. That laugh you shared. It still echoes because it never stopped. It lives in the frame where it occurred. And one way to think of death, not poetically but scientifically, is as the moment your consciousness reaches the last frame in its slice of the block. You don't disappear. You complete. And someone watching from outside, some hypothetical being who could see all of spacetime at once, would see you fully. Not as a flicker, but as a structure. A complete being with a defined path through the universe. And maybe that's enough. Maybe the fear of time running out only exists because we believe it runs at all. But in the block, nothing runs. Everything is. And the moment you're in right now. It's not fleeting. It's permanent. It's real. Even if you never feel it again. Because in the block, you always will. Time travel stories are full of warnings. Don't touch anything. Don't talk to anyone. Don't kill a butterfly. The fear is always the same, that one small change in the past could ripple forward and collapse the future. But what if that's not how time works? What if the timeline doesn't just allow changes, but repairs itself? This is the idea behind the self-correcting timeline hypothesis, the notion that time as a system resists paradox, that when something or someone tries to alter the past, reality adjusts, bends, and subtly shifts until the outcome stays the same. Not because it's fixed, but because it's resilient. Let's say you travel back to stop a car crash that killed someone you love. You find the street, you warn the driver, you redirect traffic, and it works. The crash never happens. But later you hear news of a different accident, same result, different cause. Or maybe the person survives the crash, but dies of a heart attack that night. Or maybe they live, but someone else dies in their place. A transfer of consequences, like reality shifting puzzle pieces to keep the overall picture intact. You feel like you made a difference. But the timeline absorbed your actions. Philosophers call this the rubber band effect of time. You stretch it, but it snaps back, not perfectly, but close enough to preserve continuity. This isn't just a sci-fi trope. It has roots in probability theory, dynamical systems, and even thermodynamics. In complex systems like weather, ecosystems, and economies, when one variable changes, the others adjust, not to reverse the change, but to rebalance, to restore stability. And if the universe is a system, a massive, entangled, interdependent machine, then it may behave the same way. Some physicists have modeled time with these ideas in mind. They suggest that certain paths in spacetime have attractors, stable configurations that the universe wants to fall back into. No matter how many times you perturb the system, the trajectory curves home. That doesn't mean nothing can change. It means only certain kinds of change can last. In the self-correcting timeline, free will exists, but it's bounded. You can make choices, but those choices are filtered through constraints that prevent contradiction. You could meet your younger self, talk, interact, but you couldn't tell them something that would prevent you from going back to meet them in the first place. Why? Because then you wouldn't be there to tell them. The contradiction never forms because reality edits it out. Maybe the conversation goes differently. Maybe they forget. Maybe circumstances shift just enough to keep the loop closed. The paradox doesn't explode, it dissolves. Now here's where it gets personal. What if this explains something you've felt before? That eerie sense that no matter how hard you try to break a pattern in your life, it comes back. that no matter how many different choices you make, you end up in the same emotional place, the same outcome, the same regret? What if your timeline is self-correcting? What if every version of you that tried to do it differently, move away, stay quiet, say yes, say no, has already happened? And each time, reality let you try, but curved everything back to where it was always going. Would you stop trying? Or would you start to wonder if maybe it's not the events that are fixed, but you? And what if, far in the future, time travel is real? What if people use it to fix history, prevent disasters, erase atrocities? And what if it doesn't work? Not because the technology fails, but because time doesn't permit it. Every attempt simply reshapes the path until the same endpoint is reached. Same wars, same mistakes, same collapses. Different reasons, different disguises, but always the same result. Because some things, once they happen, don't just belong to history. They become part of the structure, and the timeline knows how to protect itself. Not with force, not with rules, but with subtle, invisible redirection. So the next time you wish you could go back and change something, stop and ask, are you sure you haven't already tried? And are you sure that trying again won't just lead you back here? You're holding two playing cards, one red, one black. You shuffle them behind your back. Then you hand one card to a friend who immediately takes a flight to Tokyo. You keep the other. Neither of you knows which card you're holding. Later, you flip yours. It's red. In that moment, without touching anything, without saying a word, your friend's card in Tokyo becomes black. It sounds like magic. But it's not. It's quantum entanglement. Two particles entangled can share a single state, even when separated by vast distances. Measure one and you instantly know the other. Einstein hated this idea. He called it spooky action at a distance. But no matter how unsettling it felt, experiment after experiment proved it was real. And yet, that was only space. What happens when entanglement stretches across time? What happens when a particle seems to know something that hasn't happened yet? That's the frontier, the unsettling territory of quantum entanglement through time. It's not a theory. It's an experiment that's already been done. And it changes everything we thought we knew about what comes first and what can come back. Let's start with something simple. Imagine you have a single photon, a tiny packet of light. You fire it through a polarizing filter and it aligns a certain way, horizontal or vertical. That's expected. Now imagine you entangle two photons. Send them flying in opposite directions. One ends up in your lab, the other 10 kilometers away. You measure yours, it's horizontal. Instantly, no matter how far apart, the other must be vertical. That's standard entanglement. But now the twist. Suppose you entangle two particles, but you don't decide to entangle them until after you've already measured one of them. That's not hypothetical, it's been tested. And the results, they match the entangled pattern. As if the future choice to entangle reached backward in time and altered the past state of the particles. It's called entanglement swapping, and it has been done. Here is how it works. You start with two pairs of entangled particles, call them 1 and 2 and 3 and 4. You keep particles 1 and 4 and send 2 and 3 into a lab. You perform an operation on 2 and 3 that causes them to become entangled after 1 and 4 have already flown off to different detectors. Now remember, 1 and 2 were never in contact with 3 and 4. But if 2 and 3 become entangled later, and 1 and 2 had been entangled before, and 3 and 4 had been entangled before, then, mathematically, 1 and 4 must now be entangled too. Even though they never interacted, even though they were never in the same space, even though their connection was decided after the fact. You can even perform this swap after you've measured 1 and 4. So it's as if the choice to entangle 2 and 3 reached backward and created a new relationship between 1 and 4 after they were already gone. Reality didn't seem to care that the decision came later. It just adjusted. This leads us to temporal entanglement, where time itself becomes part of the quantum state. In 2013, a team at the Hebrew University of Jerusalem published a groundbreaking study. They entangled photons that never coexisted. One photon was created and measured. Then it was gone. Later, another photon was created, and somehow it was entangled with the first. That shouldn't be possible. Entanglement requires a shared event and interaction. But here, the two photons existed at different times. They never met. The first was already absorbed, destroyed, collapsed. And yet, when you measure both systems, you find correlations, the kind of results you'd expect only if they had been entangled. This isn't just coincidence. The math works out. The experiment repeats. Something is happening that suggests quantum systems can link across time. Not metaphorically, not in science fiction. In the lab. Now pause for a moment. What does this mean? Is it really possible for something in the future to define something in the past? If a decision made in 2025 can affect the state of a particle measured in 2024, what does that say about causality? What does that say about free will? You're probably thinking this is just particles, it doesn't apply to us, we're too big, too messy. But here's the uncomfortable truth. You are made of particles. Your thoughts, your memories, your body are built from atoms obeying these same quantum rules. And if particles can be entangled through time, what stops entanglement from threading your mind? There's a thought experiment some physicists like to play with. Imagine you're faced with a decision. You can choose option A or option B. You hesitate, you weigh your feelings. You recall a memory from years ago, an image, a face, a moment of shame. That memory pushes you toward option A. But what if that memory wasn't from the past? What if it only emerged because, in the future, you choose option A? And your brain, your mind, your internal quantum machiner, why, is stitching that decision backward into memory. You wouldn't feel anything unusual. It would feel like you remembered something that influenced your choice. But in truth, the choice caused the memory. This is retrocausality, the idea that an effect can come before its cause, if cause and effect are entangled in a non-classical way. And we don't have to go into the metaphysics to feel it. How many times have you had a memory rise from nowhere, just in time to guide you? How many times has a person appeared in your thoughts, right before they re-entered your life? How many times has a déjà vu felt like a message? Maybe it wasn't from the past. Maybe it was a message from you in the future. And maybe that message isn't a miracle. Maybe it's just physics. Now let's push even further. In some interpretations of quantum mechanics, the universe is fundamentally non-local. That means events don't just happen in isolated chunks. Every piece of information is connected to every other, not just across space, but across time. Physicist Yakir Aharonov has spent his life developing the two-state vector formalism, a way of describing quantum systems not just by what's happened, but by what will happen. In this view, a quantum particle is described by two wave functions. One coming from the past, as usual, and one coming from the future, traveling backward in time. The present, then, is a point where past and future interfere, where information from both directions meet. This isn't science fiction. It's peer-reviewed, experimentally viable physics. It means the future doesn't just passively wait to happen. It reaches back. And if that's true, it reshapes how we understand everything. A decision isn't just influenced by what you remember. It's influenced by what you will know. A photon doesn't just react to where it's been. It reacts to where it's going. The universe doesn't just evolve forward. It converges from both ends into something coherent, something timeless. So what would it mean to live in a world like this, where entanglement isn't bound to place or moment, where your life isn't a line from birth to death, but a tapestry of cross-threaded timelines, influencing each other in ways you'll never fully see. It would mean that fate isn't a prison. It's a feedback loop. And your deepest intuitions, your strangest thoughts, your most inexplicable urges might not be irrational at all. They might be messages from the version of you who already lived this. Who made the decision? Who sent the signal back? It's easy to dismiss this. Too abstract, too quantum, too weird. But you don't have to understand quantum physics to feel its pull. You just have to notice the patterns. That moment you looked up from your phone and locked eyes with someone just before they spoke. That second you stopped walking for no reason and avoided a crash. That uncanny feeling that this has all happened before, not like a memory, but like a loop finally closing. Maybe these are just coincidences. Or maybe, deep beneath the surface of ordinary cause and effect, you are already entangled with who you're about to become. Quantum entanglement through time doesn't let us build a time machine. But it does hint that time isn't what it seems. That the past is not fully gone. That the future is not fully separate. That now is not the only place where you are. And if some part of your life has already sent out echoes, what part of you is listening for them now? And what will you do when you hear them? It begins where it ends, and ends where it begins. The ancient symbol of the Ouroboros, a snake eating its own tail, has existed for thousands of years. You've seen it carved in stone, etched into alchemical scrolls, drawn into secret symbols across centuries and cultures. It represents eternity, wholeness, a cycle with no start and no stop. But what if it's more than myths? What if it's the actual shape of time? Not metaphorically, literally. What if the universe itself is a loop? A cosmos that doesn't expand into nothingness and fade, but one that circles back, folds inward and starts again, not after it ends, but through its ending. This isn't poetry. It's a serious scientific model. And it changes how we think about everything, from the Big Bang to the very nature of time itself. The traditional story of the universe is this. About 13.8 billion years ago, there was the Big Bang, a singularity, an infinitely small, infinitely dense point. From it, everything exploded outward: space, time, matter, energy. Since then, the universe has been expanding. Galaxies race away from each other, the fabric of space stretches, stars burn out, black holes consume. Eventually, everything will cool, slow, and go dark. This is called heat death, a final, frozen stillness. A lonely end. But some scientists began to wonder, what if it doesn't stop there? What if that ending is just the next beginning? Enter the Big Bounce model. Instead of a singular birth followed by death, the Big Bounce suggests that the universe goes through cycles, expanding, collapsing, and bouncing back again. Boom, crunch. Like a heartbeat. Like breath. But the Ouroboros model goes further. It doesn't just suggest that the universe restarts. It suggests that the end is the beginning. That the next universe isn't separate from ours. It is ours. Played backward. Here is how that might work. Imagine time as a line stretching from left to right. That's how we usually see it. But in the Ouroboros model, time doesn't go left to right. It curves, it loops. When the universe reaches its final moment, maximum entropy, maximum expansion, it doesn't just stop. Instead, something happens, a phase change, a flip. Entropy resets, and the arrow of time reverses. From that moment forward, every particle begins to move in the opposite direction. Events unfold backward, deaths become births, collisions unwind, galaxies retract. But here's the twist. For the beings inside that reverse timeline, us, reborn, we don't notice anything strange. Because our thoughts, our memories, our physics all follow the new arrow of time. To us, it still feels like we're going forward. So when the end becomes the beginning and the loop completes, we live it again. Not as a replay, as a return. This sounds wild, but it's rooted in real physics. You see, the laws of nature, the equations that govern motion, force, and particles, are mostly time-symmetric. Meaning they work the same forward and backward. If you filmed two particles colliding and then played the tape in reverse, you wouldn't know which was the real direction. The only major exception is entropy, the rule that disorder increases over time. That's why broken glasses don't reassemble, why smoke doesn't go back into the cigarette, why you remember the past, not the future. But in the Big Bounce or Ouroboros models, even entropy plays along. At the point of maximum disorder, heat-death, the universe becomes so uniform, so stable, that there's no more difference to detect, no more increase, entropy plateaus. And when it flips, the increase of order feels like new entropy in the other direction. Everything works. It's a mirror. So what does this mean for time travel? It means that we may already be doing it. That every time you live a life, you're not moving toward a singular end. You're moving through one loop in a cycle that never breaks. A return, not a repetition. Your choices matter, but they're folded into a structure that transcends sequence. This also raises a deeper question. If the universe is a loop, does anything truly change? Imagine this. You're born in a hospital room, your mother holds you, a clock ticks, you grow up, make mistakes, fall in love, break someone's heart, regret, heal, learn, laugh, sleep, age. And one day you lie on a bed in another room, breathing slows, a final thought, silence. From the outside, your life has passed. But from the inside, you are still moving. Your final thought blends into your first breath. You begin again. But it doesn't feel like déjà vu. Because the structure of the loop isn't just circular, it's self-reflective. Each pass changes its own conditions. Each version of you, though similar, is not the same. Like a melody that returns to its root note, changed, enriched, deeper. The same universe, but not quite. The same life, but with something learned. In this way, the Ouroboros universe is not a prison. It's a classroom. And time is not linear. It's recursive. You don't escape by leaving the loop. You transcend by understanding it. Scientists are still grappling with how to test this. If the universe is looping, how would we know? Some theories predict subtle asymmetries in the cosmic microwave background, the radiation left over from the Big Bang. If this is actually a bounce or a reversal, we might find clues in its structure. Others look for gravitational echoes, patterns in how galaxies cluster or how black holes evaporate. But maybe the most important evidence is inside us. That strange feeling you've been here before. That intuitive knowledge you can't explain. That sense of purpose that seems too deep for one life. If the Ouroboros is real, then your existence isn't a straight line. It's a spiral. And here's the most haunting part. If time is a loop, then maybe nothing is ever truly lost. Every word you've spoken, every person you've touched, every version of yourself you thought was gone, they're still there, waiting at the turn, waiting to meet you again. So the question is not, can we time travel? The question is, have we already? And if this is your second time through, what are you supposed to do differently now? You're standing on a massive spinning platform. Imagine something like a carousel, wide as a city, slowly rotating under your feet. At the center stands your friend, Anna, calm, unmoving, right in the middle of the disc. You're near the edge, feeling the force tugging you outward. You both wear identical atomic watches. You sync them. You wave to Anna and begin walking around the disc's edge, keeping pace with its rotation. It feels slow, steady, nothing strange happens. You make a full loop and return to Anna. You look at your watch, then hers. They don't match. Yours is behind. Even though you were together, even though you both experienced the same amount of time, At least, it felt that way. This is not a trick. It's not a malfunction. It's a real, testable effect. It's called the clock paradox on a rotating disk, and it reveals something unsettling. Time doesn't pass the same for everyone, even in the same place, doing something as ordinary as turning in a circle. Let's step back. We're used to thinking of time as steady, reliable, like a river flowing at the same speed for everyone. But in Einstein's world, that's not true. According to special relativity, time slows down the faster you move. This is called time dilation. It's been tested with satellites, particle accelerators, and atomic clocks. It's real. If you're moving, time passes slower for you compared to someone standing still. Now, imagine applying that to a rotating platform. At the center, Anna is still. But you, on the edge, are moving in a circle. Even if you don't feel like you're moving fast, you're technically covering more ground per second. That's velocity, and that velocity affects your experience of time. From the outside, a scientist observing the whole disk would say, Anna's clock ticks normally. Yours ticks slightly slower. And not just theory, this has been measured. In the 1970s, researchers flew atomic clocks on airplanes around the world. When they landed, the clocks were compared to identical ones on the ground. The flying clocks ran slower. Even a difference of microseconds was detectable. That's how precise time really is. And how fragile. But here's the twist. This isn't just about speed. It's about direction, rotation, and the strange properties of spacetime when it spins. When you're rotating, your frame of reference is non-inertial, meaning you feel forces that someone standing still wouldn't. Like when you're in a turning car and feel pushed sideways. That's not real gravity, it's a result of motion. On a rotating disk, those forces bend not only your path, but time itself. This leads to the Sagnac effect, a phenomenon where light sent around a rotating loop returns at different times depending on direction. It's used in GPS systems, gyroscopes, even airplane navigation. You send light clockwise and counterclockwise around the disk. When it returns, one beam gets back slightly before the other. Why? Because the platform moved under the light. It's a tiny difference, but measurable. And it proves rotation twists time. Now imagine extending this to a cosmic scale. Think of a rotating black hole. According to general relativity, a spinning black hole doesn't just pull in space. It drags time itself around with it, a phenomenon called frame dragging. If you could orbit close enough to such a black hole and time it right, you might loop through space so fast and so curved that you return to the same point before you left. This is the basis of one of the wildest time travel ideas, using the extreme rotation of spacetime to close a loop, what physicists call a closed Timelike curve. The rotating disk is the humble version of that. But the principle is the same. Motion bends time. Rotation twists it. And what looks like a simple spin might be a doorway. So why does this matter? Because it tells us that time is not a background. It's not some absolute clock ticking independently of everything else. Time is part of the structure of space. It flexes. It yields. It warps around motion. Even circular motion, something we experience every day. And that has consequences. Imagine a space station orbiting Earth, spinning to generate artificial gravity. The people living near the edge, where the spin is strongest, would age slightly slower than those near the center. Not in science fiction. In reality. It's not enough to notice day by day, but over years, decades, the gap adds up. In principle, if someone lived their whole life at the edge of a fast-rotating space ring, and you lived in the middle, they could be biologically younger than you when you're both 80. Time doesn't just flow. It's shaped by where you stand and how you move. There's something deeply unsettling about that. You can be born in the same place, under the same stars, breathing the same air, and still live a different amount of time just by moving differently. It makes you wonder, what else is bendy? and G beneath us. What other subtle motions, fields, or rotations are distorting the seconds we think are solid? Maybe it's not just black holes or cosmic disks. Maybe time is already warping around us, quietly, every time we spin in a chair, turn a corner, or circle back to someone we thought we left behind. In the end, the rotating disk isn't a time machine, but it's something even more intimate. Proof that time is not fixed. That even in ordinary, physical, repeatable settings, like a spinning floor, it refuses to stay straight. And if a clock on your wrist can fall behind just by turning in place, what does that mean for your memories, your future, your sense of self? You're not just aging forward. You're spiraling through time, space, and motion on a disk so big you can't see the edge. And the center. You'll never reach it. Because every step you take warps time just enough to keep you chasing it forever. Try to picture the beginning of time. Not metaphorically, literally. Picture the exact moment when time itself began, when there was no universe, no matter, no light, no space, no direction, no clock ticking, no before. And then suddenly there was something. Time began. The universe exploded into being. This is the classic image of the Big Bang, a singularity infinitely dense, infinitely small, impossible to understand, sitting at the very start of everything. But what if that image is wrong? What if time never really started in the way we imagine? What if the universe didn't come from a point, but from a curve? What if there was no singularity, no bang, and instead the beginning of time was smooth, finite, and boundless? This is the core of the Hartle-Hawking no-boundary proposal. It's not just a clever theory, it's a radical shift in how we think about the past. Because if they're right, then the question what came before the Big Bang makes no sense. There was no before. Not because it's forbidden. Because the concept itself is meaningless. This theory comes from physicist James Hartle and the late Stephen Hawking. Together, they tried to answer the deepest possible question: how did the universe begin? But unlike many cosmologists, they didn't start with space. They started with time. And they asked, what if time is more like space than we think? Let's try to make that concrete. Imagine you're standing at the North Pole. Every direction is south, there's no further north. It's not that the world ends there, it's just that north of the North Pole doesn't make sense. That's what Hartle and Hawking proposed for the universe. That time didn't have a sharp edge. That the Big Bang wasn't a wall, but a rounding. A smooth surface where time slowly transformed from something different, something not time, into what we now experience. They called this a Euclidean beginning. Here is how it works. In ordinary physics, time behaves differently than space. In equations, time is treated with a minus sign, while space uses a plus sign. This reflects how things move and evolve. But what if, at the very beginning, there was no difference? What if time was imaginary? In math, imaginary time means time that behaves like space, without direction, without flow, without causality. In the Hartle-Hawking model, the early universe wasn't a tiny ball of fire exploding into something. It was more like a four-dimensional sphere, a curved surface that had no boundary, no edge, and no singularity. No moment of zero time. Just smooth geometry. And eventually, this curved, imaginary time structure transitioned into real time, the kind we experience now, with days and seconds and death. Why does this matter? Because it solves one of the most disturbing problems in cosmology, the singularity. In standard Big Bang models, the universe starts from a point of infinite density. That's a math problem, a breakdown. Physicists hate singularities because they signal a failure in the theory. The Hartle-Hawking proposal removes the singularity. It replaces it with geometry, with a smoothness, with a universe that simply is, without needing a cause or a before. Let's return to our North Pole analogy. When you walk south from the North Pole, you trace lines across a sphere. You can describe every point, every coordinate. But the pole itself, it's not a point of failure, it's just a different kind of place. A place where directions lose meaning. That's how this model treats the beginning of time. It wasn't an explosion. It was a transformation. From a realm of geometry to a realm of physics. From timelessness to time. Some people misunderstand this theory. They think it means time is infinite or that the universe is eternal. But that's not quite it. Time still has a starting point in the sense that there's a limit to how far back we can go, but there's no edge, no singular moment where something had to begin. Instead of a cliff, it's a hill. And when you reach the bottom, you don't fall off. You just realize there was no top. Only smoothness. Only curve. And here's where it gets strange. Because if time didn't begin with a bang, then what does that say about causality? About creation? About God? Philosophers and theologians have long debated the idea of a first cause, something that brought the universe into being. But the no-boundary proposal suggests that question might be meaningless. Not because the answer is unknowable, but because the question is malformed. It's like asking what's north of the North Pole, or what's before the beginning when before didn't exist yet. In this model, the universe doesn't require a creator. It just is. Its existence is not the result of something else. It's a result of how geometry works. Now let's tie this back to time travel. Because you might be thinking, okay, this is about the beginning, but how does it help us move through? Time. Here's the answer. If time is not fundamental, if it emerges from a deeper structure, then time travel may not require breaking physical laws. It might only require accessing the structure underneath. Think of it like this. If you live on the surface of a sphere, you can walk forward, backward, left, right, but you're still bound to the surface. But what if you could move through the sphere? What if the past and future aren't back there or ahead, but part of a deeper layer you can dip into? Maybe the arrow of time is just a path on the surface. But the true shape of reality is deeper. And curved. And open. There's one more haunting implication. If the universe has no boundary, then maybe your story doesn't either. Maybe you're not a linear life with a start and stop. Maybe your existence is part of a wider shape, something that curls back on itself, loops through experience, and emerges again. Not because you reincarnate. Not because you're reborn. But because, fundamentally, you never ended. You just curved. You just transformed. You just passed through a region where time didn't make sense. Until it did again. So the next time you ask, how did it all begin? Maybe the answer is, it didn't. It rounded. And you are still walking the curve. Let's say someone you love goes into surgery. It's a risky one, maybe heart-related, maybe brain, and they're unconscious, vulnerable, surrounded by machines, strangers, and the quiet hum of sterilized time. You wait. You hope. You pray. This is familiar. People have been doing it for thousands of years. But what if you prayed for them not before the operation, but after? What if the surgery was already done days ago, and you still bowed your head and asked for a good outcome? Does it matter? Is that ridiculous? Or is there something we don't fully understand, not just about prayer, but about time itself? This question isn't just philosophical. It was tested in a real, peer-reviewed medical study, where people prayed in the present for surgeries that had already happened in the past. And somehow, the results changed. Let's back up. The year is 2000. A physician named Leonard Leibovitz conducts a strange, double-blind study at the Rabin Medical Center in Israel. His goal, to test whether prayer could affect the health of people with serious blood infections. The twist. The patients were from 1990 to 1996, years earlier. They had already been treated. Their outcomes, including how long they stayed in the hospital, how many died, were already decided, already written, already part of the hospital's database. The prayers came later. Random people unaware of the patients' identities were asked to pray for some of the patients. Not all, just a randomly selected group. No one involved in the care of the patients knew. The patients themselves had no idea. The data was locked. Then, once the prayers were said, researchers opened the files and compared the two groups. The result: the group that had been prayed for after the fact had shorter hospital stays, lower fevers, lower death rates. And it wasn't just statistical noise. The differences were significant. Meaning, according to normal scientific standards, something had happened. But how? The events were already in the past. The treatments were done. How could words spoken today affect patients from 6 years ago? The immediate response was skepticism, of course. Scientists assumed it was a fluke, a methodological error, or a misunderstanding of the statistics. Maybe the data wasn't truly random. Maybe the prayer group just happened to contain patients who were less sick. Maybe it was all just a coincidence. But there was a problem. The study had been well designed. Not perfect, no study is, but solid enough to appear in a serious medical journal. And it raised an uncomfortable question. What if causality isn't what we think? In physics, there's a concept called retrocausality. It means that future events can affect past ones. This sounds impossible until you get to quantum mechanics. There, the rules change. Experiments like the delayed choice quantum eraser show that a decision made after a particle has passed through a slit can determine whether it behaved like a wave or a particle beforehand. It's real. It's measurable. It's been repeated. And it means that our understanding of time, of cause and effect, is not fixed. That maybe, under certain conditions, the future can influence the past. So let's return to prayer. Let's strip away the religious implications for a second. Think of it as a conscious intention directed toward an event that already occurred. If reality is more like a network than a line, if events are entangled across time, if information can move backward under certain conditions, then maybe intention is not as limited as we think. Maybe it doesn't matter when you focus. Only that you do. Of course, this doesn't mean prayer always works, or that you can change history at will. But it does mean we need to rethink what it means for something to be in the past. Because if that word only means earlier in time, and time itself is flexible, then the past is not gone. It's still there. Still open in some sense. Still responsive. Just hidden. Let's play with an analogy. You write something in a document. You hit save. You think it's done. But then, a few days later, an app on your computer goes back and changes a line, not with your knowledge, not in the current version, but in the file from last week. You reopen it, and the sentence you remember writing is different. Not because someone broke in, not because of memory loss, but because the system allows retroactive edits. What if the universe is like that? What if your experience of time is just your version of the document, and there's a back-end process running beneath it, allowing changes from moments you haven't even reached yet? And what if certain kinds of thoughts, focused, intentional, emotional, leave traces in both directions? Now you might say this is dangerous thinking. It opens the door to magical ideas. It blurs science and belief. And you'd be right to be cauty. The retroactive prayer experiment is controversial. Some scientists dismiss it outright, others think it should never have been published. But here's what matters. It was published, and it showed something we weren't ready for. Not proof of miracles, not evidence of divine intervention, but a subtle crack in the structure of time. A moment where cause did not obey the rules. A place where the arrow bent. What can we do with that? Maybe nothing. Maybe it's an anomaly, a glitch in the noise. Or maybe it's a clue. That time isn't a straight path. That memory is more than recall. That your thoughts even now, even here, might echo backward. And that the past, however sealed, still listens. Imagine this. You sit in a chair in a sealed room. In front of you is a machine, a strange, silent device connected to a quantum particle. It's programmed to perform a simple task. Every time the particle is measured, it randomly collapses into one of two possible states. If it collapses into state A, nothing happens. If it collapses into state B, the machine pulls the trigger. The gun fires. You die. Now imagine repeating this process over and over. You sit down. The particle is measured. The machine clicks. Sometimes it fires. Sometimes it doesn't. But here's the twist. You never experience the moment when it does. Not because the machine is faulty. Not because the experiment stops. But because, from your point of view, you always survive. This is the core of the quantum suicide thought experiment. A dark, extreme cousin of Schrödinger's cat. It's not about probability, it's about perspective. Because in quantum physics, specifically in the many worlds interpretation, every possible outcome of a quantum event actually happens. When the particle is measured, the universe splits. In one universe, you die. In the other, you live. And the only version of you that continues to observe anything is the one that lived. So no matter how many times you run the test, your consciousness only travels through the worlds where the gun doesn't fire. Now pause. This is not a science fiction story. It's a real interpretation of quantum mechanics, proposed by Hugh Everett in the 1950s, that has gained serious traction. In the many worlds view, the universe doesn't collapse when a quantum event occurs. It branches. There is no single timeline. Only a constantly splitting tree, infinite, sprawling, unimaginable. And each version of you follows a path through those branches. Most end in the ordinary ways. But one line, always one, continues. This leads to something eerie. Quantum immortality. The idea that from your own perspective, you never die. That no matter what happens, car crash, heart attack, experiment gone wrong, there is always a version of reality, however unlikely, where you survive. Where your heart keeps beating. Where the bullet misses. Where the disease mysteriously disappears. You don't get to choose the path. You don't control the odds. But your experience, your thread of consciousness, always follows the line where you remain alive. To you, subjectively, death is something that only happens to others. Because you can't observe your own non-existence. But here's the nightmare hidden inside the miracle. If this is true, then your survival is inevitable. But not pleasant. Over time, the universes where you continue living become increasingly rare, increasingly improbable, and potentially increasingly awful. You survive the car crash, but with injuries. You beat the disease, but in agony. You grow older, weaker, more alone, but never quite reach the end. Because in every moment where death is possible, there's always one thread where you survive. Even if it's barely survival. Even if it's suffering. Even if it's just a mind in a body that refuses to die. This flips the idea of immortality on its head. We imagine it as a gift, a superpower. But quantum immortality is not romantic. It's cold, mechanistic, inevitable. It doesn't care about your happiness, or your pain, or your dignity. It simply ensures that there is always a version of you still observing, because in the many worlds model, the flow of consciousness is tied to existence, not to comfort. And that version continues, even as the odds grow astronomical. Even when the body breaks, even when everyone else is gone, you remain. Let's return to the gun. You sit in the chair. The machine measures the particle. The gun clicks. You hear it misfire. Again and again and again. To anyone watching from the outside, it's random. Sometimes you're gone. Sometimes you live. But from your perspective, the machine never fires. You never die. And each time it clicks, each moment of near death, only deepens the illusion of invincibility. Until you wonder, how far can this go? How long can the threads stretch? And what does it mean to be trapped in the version of reality where you never escape? This thought experiment isn't meant to be tested. It's not a proposal. It's a mirror. A way of revealing the strange, counterintuitive consequences of quantum theory, not through math, but through mortality. It forces you to ask, what is a self? What is observation? And if every moment of choice spawns a new world, then who are you really? The sum of all your versions, or just the one that keeps going? In the end, quantum suicide is not about dying. It's about what it means to continue. To face a universe where, for you, there is no final breath. No curtain. No release. Only the long, improbable road of survival through disaster, decay, and the low crumbling of probability itself. And if that sounds comforting, you haven't thought it through. Because immortality without peace, without end, without silence, is not life. It's a question, with no one left to answer it. You're sitting still, not moving. Maybe you're staring at a wall, nothing is happening. And yet, inside your head, something strange is unfolding. You're suddenly thinking of next week, the meeting you forgot, the birthday you have to remember, the question you might ask someone in just the right moment. A second later, you're gone again, back to 3 years ago, reliving a conversation you keep rewriting. You know it's over, but you're still there, correcting what you said, rehearsing what you should have said. You're not time traveling in a machine, but you're not exactly here either. That ability to project your mind into the past or future is called chronesthesia. And it may be the only form of time travel that we truly and undeniably possess. Chronesthesia isn't imagination. It's not fantasy. It's the mental capacity to experience oneself in another time. Psychologists describe it as mental time travel. Not metaphorically, but functionally. It uses different brain structures than daydreaming or visualizing. When you remember the past, you don't just retrieve data, you simulate being there in a first-person sense. And when you think about the future, you simulate being there too, with all its uncertainty, emotion, and possibility. In other words, you don't just picture the event. You insert yourself into it. You generate a conscious version of yourself in another point in time and run it. This sounds trivial, but it is. Because your sense of identity, your feeling of who you are, is not built from the present alone. It's built from this constant movement between what was, what is, and what might be. You aren't a fixed person. You're a traveler. And the road is inside your mind. Neuroscientific research has found that certain regions of the brain light up when we engage in mental time travel, including the default mode network, a set of interconnected areas that also play a key role in introspection, empathy, and even moral judgment. In other words, the same system that allows you to think about who you are is the one that lets you leave the present. Chronesthesia isn't a side effect of thought. It is thought, at least the kind of thought that makes us human. But here's the paradox. If your mind is always moving through time, then when are you ever really here? How many hours have you spent in moments that were already over, reliving old arguments, regretting old decisions, replaying memories as if you could change them? How many more have you spent in moments that haven't yet come, anticipating failure, imagining praise, fearing a future that might never arrive. In a sense, your mind is a time traveler that never stops jumping. And sometimes, it forgets to land. This creates a strange feedback loop. Because every time you visit the past, you alter it. Not factually, but emotionally. Memory isn't a recording, it's a reconstruction built anew each time. When you remember a moment, you don't just retrieve it. You rewrite it with who you are today, how you feel now, and what you need the memory to be. So every act of mental time travel changes the past. Not out there, but in you. And if your emotional reality is shaped more by remembered and imagined times than by the present, then isn't time travel already happening? There's more. This ability to mentally time travel can be lost. Patients with certain brain injuries, particularly to the hippocampus, report being trapped in the present. They can't remember the past as themselves, nor can they imagine specific futures. They don't feel sad or nostalgic or hopeful. They're alive, but not traveling. Their consciousness has become a point, not a line. A presence, but not a path. And in losing that path, they lose something of their humanity. So here's the question. If you can't stop your mind from time traveling, if you're constantly bouncing between times, reshaping meaning and identity through memory and projection, then are you ever really just now? Or are you always elsewhere? And if time is only truly experienced through the mind, then maybe the body stays still. But the self never does. Chronesthesia is not a machine. You don't need wires or formulas. You don't need paradoxes or wormholes. Because your own brain is already doing the impossible. It's moving backward. It's leaping forward. It's running simulations of you that don't and may never exist. And it does this all day, effortlessly. So maybe the reason we dream of time travel is because some part of us knows we already do it. In a dark lab buried deep beneath the noise of the outside world, a beam of light is sent down a narrow tunnel. It travels quickly as expected, but then something happens that shouldn't. The light doesn't just slow down or bounce off an obstacle, it appears to reverse, as if it had been reflected by nothing, as if the future pulse had sent information backward. This is not science fiction. It's an actual experiment, replicated multiple times, that seems to defy the basic order of time. And it forces us to ask, what if light itself, the thing that defines our limit of speed and causality, isn't bound to one direction? What if time for light is a two-way street? Let's start with how light normally works. In school, we're told that light moves at a fixed speed, roughly 300,000 kilometers per second in a vacuum. It's the cosmic speed limit. Nothing outruns it. And everything that happens, cause and effect, is built around this fundamental law. But light isn't just a speed, it's a wave. It has peaks and troughs, it can interfere, reflect, refract. And under certain conditions, it can do things that feel impossible. Like move backward. In 2006, a team of physicists at the University of Rochester performed an experiment with a phenomenon known as time reversal of a light pulse. Here's what they did. They sent a pulse of light into a special kind of optical fiber, one engineered to manipulate the light's behavior. Then they applied a process called phase conjugation. In simple terms, this process takes the wave, which normally propagates forward, and creates a mirror image of it, but not spatially. Temporally, it's as if the wave was flipped in time. And what emerged from the fiber wasn't just a reflection, it was a reversed copy of the original signal, retracing its path backward. Like watching a movie of the event in reverse, but in real life. Why does this matter? Because light is how we measure time. A clock is just a device that counts vibrations of light. A mirror reflects a moment. A photograph captures a delay. So when light moves backward in time, even just mathematically, it challenges the deepest assumptions we have about cause and effect. Of course, no one is claiming that entire objects traveled through time in these experiments. What happened was more subtle and more disturbing. The information inside the light, its structure, its pattern was reversed. It returned to its origin, not spatially, but temporally. And this raises a powerful possibility that the universe is not one way. That time, like space, may be symmetrical at its most fundamental level. And what we experience as forward is just one bias among many. The concept of time symmetry is not new. In fact, many of the core equations of physics, especially those describing electromagnetism and quantum fields, are time reversible. That means if you replace t with t in the formulas, the math still works. The laws don't care whether time is going forward or backward. Only our experience does. And that experience of causes leading to effects may not be built into the universe. It may be built into us. So where does this leave us? If a pulse of light can be reversed in time, if the universe allows information to flow backward, if time reversal symmetry is a real physical property, then what are the limits? Could you send a message into the past? Could two particles communicate in both directions? Could your future self leave you clues? Maybe not in the form of spoken words or visible signals, but in tiny imbalances, in quantum probabilities, in subtle corrections that echo backward from what will be into what is. This is not about magic. It's about what happens when you stop assuming that time is straight. The time-reversed light pulse experiment doesn't tell us how to build a time machine. But it does tell us this. Time may not flow like a river. It may ripple. It may bounce. It may fold. And sometimes, if you listen closely enough, you can hear the echo of something that hasn't happened yet. Not in the sound, but in the silence it leaves behind. There's a question that most people never ask, not because it's hard to answer, but because it feels wrong to ask. What if cause doesn't always come before effect? What if something in the future can reach back and change the past? It sounds like a paradox, but it's not. It's a legitimate, ongoing area of research in quantum physics. And the more closely scientists look, the more they start to wonder not if retrocausality is possible, but if it's already happening. Let's start with the basic intuition we all share. You drop a glass, it shatters. You light a match, it burns. Things happen in order. Time moves forward, causes lead to consequences. The past is fixed, the future is open. Right? Well, not so fast. Because in the realm of quantum mechanics, the order of cause and effect is not always clear. And in some cases, the arrow of time disappears entirely. One of the earliest and most unsettling examples comes from a thought experiment called the two-state vector formalism, proposed by Yakir Aharonov and his colleagues. In this view, a quantum system isn't fully described by just its initial conditions, what you measure at the start, but also by its final conditions, what you measure at the end. In other words, the state of a particle isn't just influenced by its past, but also by its future. The idea is shocking. It's like watching a game of billiards and realizing the balls didn't just move because you hit them, they also moved because of where they'll end up. That's not just poetic. That's physics. In 2012, an actual experiment was conducted that pushed this idea into reality. A team of researchers used entangled photons in a setup where a decision made after a particle had already entered a system seemed to affect the result before the decision was made. This is known as the delayed choice entanglement swapping experiment. Here's the simplified version. Two pairs of entangled photons are created. One photon from each pair is sent to separate observers, Alice and Bob. The other two are sent to a third location, where an experimenter decides whether to entangle them, but only after Alice and Bob have made their measurements. And yet, the choice made later seems to change the correlation observed earlier. It's as if the future decision retroactively decided the past behavior. How can this be? One interpretation is that there's no retrocausality, just quantum weirdness and non-locality. But another, increasingly studied view is that quantum events are time-symmetric. That the universe doesn't care whether the signal goes forward or backward. That information can, under very specific conditions, propagate from the future into the past. Not enough to send a clear message, but enough to raise a terrifying possibility. That your present is not just shaped by your past choices, but by your future ones too. Think about that for a second. Every moment of your life, every decision you think you're making freely, might already be partially constrained by what you'll do later. You're not just a product of your memories. You're a product of your intentions, of things you haven't yet chosen. And the future is not simply waiting to unfold. It may already be shaping the present, quietly, invisibly, through the rules we don't yet understand. Retrocausality doesn't mean you can send an email to yesterday. But it might mean that probabilities shift based on what's to come. That reality adapts in subtle ways. There are theories in quantum gravity and time-symmetric formulations of physics that suggest particles can have advanced waves, signals that move backward through time. They coexist with retarded waves, the ones we're familiar with. And together they form a feedback loop. A handshake across time. The implications of this are staggering. What if certain historical events, accidents, discoveries, moments of luck, were only made possible because of their future consequences? What if Beethoven finished a symphony not only because of his past genius, but because someone in the future would hear it and be moved? What if your next big insight, the moment of clarity you're waiting for, isn't born in the past, but sent backward from the future you're becoming? It sounds mystical, but it's math, and the math doesn't blink. Of course, there are limits. You can't build a time machine out of this. You can't undo a tragedy or rewrite a choice. But if retrocausality exists, even in the smallest degree, then everything changes. The arrow of time bends. The past becomes porous, and the future becomes a partner, not a destination. You might already be feeling it. That strange intuition that something ahead of you is pulling you forward. That moment sometimes feel meant to happen. That choices made now seem to ripple backward through memory. Maybe it's not magic. Maybe it's the physics of time whispering in reverse. A signal, a nudge, a loop, not a line. And maybe, just maybe, you're not just walking into your future. Your future is already walking toward you. You open your eyes. You don't know why, but something feels off. Everything looks the same, your room, the time on the clock, the shape of your thoughts. But there's a strange familiarity you can't explain, like you've done this before. Not just this moment. The whole thing. Your life. You shake it off, just déjà vu, a glitch, the brain playing tricks. But what if it is? What if the reason it feels like you've lived this all before is because you have? And what if when you die, you wake up at the start of your life again, with no memory, trapped in a loop? That's the idea behind the consciousness-time loop hypothesis. And once you think about it, it's almost impossible to unthink. Let's begin with a question. What happens after you die? Most people imagine some kind of afterlife or eternal sleep or the permanent stillness of nothing. But here's the problem with nothing: you can't experience it, you can't feel it, you can't even be aware that it's happening. Because experience, awareness, requires time. So here's the eerie part. If time stops when you die, you wouldn't notice. And if anything happens at all, if consciousness continues in any form, then from your point of view, something must still be happening. But what? Some theories, including interpretations of quantum immortality, suggest that subjective continuity doesn't end, not from your own perspective. You might die in one reality, but in another branch, one you're not aware of, your consciousness continues, slipping into a version where you survive just a little longer. And that repeats forever. But what if you don't move forward into alternate futures? What if you go back? Not your body, not the world, just your consciousness, restarting at the beginning, like a game loading from the first level, with no save points, and no memory of the last try. This idea has roots in ancient philosophy. Nietzsche called it eternal recurrence, the possibility that you will live your exact life again and again, forever. Not metaphorically, literally, every pain, every joy, every mistake. Over and over. The same sequence. The same script. You wouldn't know it, but it would happen. Endless. Identical. Inevitable. In the consciousness time loop hypothesis, this recurrence is tied not to metaphysics, but to the structure of experience itself. Consciousness doesn't have a location in space. It has a location in time. And if that time is circular, or if time at death curves back inward, then the stream of awareness may re-enter the same pattern. Like water in a looped pipe, the flow never stops. It just keeps circulating. You might ask, why this life? Why wouldn't you be reborn into a new one? Here's the twist. Because the only life you can ever be aware of is this one. Your consciousness can only occupy the timeline that leads to you being aware of it. If there are billions of timelines, you only ever wake up in the one that creates the conditions for your awareness to exist. And if those conditions arise again, exactly, the same awareness may emerge again too. Not as a copy, but as a continuation. This doesn't require reincarnation, or religion, or even physics beyond what we already know. It just requires a different way of looking at time. Not as a straight line, but as a closed loop, one that bends back on itself, sealing off the end by connecting it to the beginning. What we experience as the forward march of time might be a treadmill. Moving, yes, but getting nowhere. And always starting over. Of course, there's no way to prove this. You don't remember your last loop. You don't get hints from your future self. But maybe that's part of the loop's design. To make it feel real. To make it matter. To make you live it fully. Because even if it's your 1000th time, it still feels like the first. And maybe that's the point. Think about your biggest regrets. The things you wish you could undo. The conversations you replay at night. The paths not taken. The words not said. If this hypothesis is true, you'll get the chance. Not with memory, but with instinct. Maybe that's where déjà vu really comes from. Not a glitch, not a coincidence, but a fragment of a pattern. Breaking through. So here's the question. If this is your life again, what would you do differently? Would you recognize the turning points? Would you make different choices? Would you be braver? Or gentler? Or more present? Because if you're truly trapped in a loop, then the only way to escape might be to live it right, all the way through, as if you'd never get another chance, even though you already have. Imagine walking into a room lined with mirrors, not ordinary ones, but ones that don't reflect your present. Instead, they reflect the decisions you didn't make, the lives you didn't live, the moments that might have been. You turn your head, and instead of your current expression, you see a version of yourself smiling at someone you never met, living in a city you've never seen, wearing clothes you never bought. One mirror shows you as a painter, another as a father, a third as a stranger walking away from a conversation you had just yesterday but didn't finish. This is the Borg's mirror room. Of course, it doesn't really exist. It's a fictional thought experiment, a blend of philosophy and physics, named after the Argentine writer Jorge Luis Borges, who often wrote about infinite libraries, labyrinths of time, and mirrored selves. But in 2014, a team of researchers at the University of Tokyo tried to test something surprisingly similar, not with literal mirrors, but with a machine learning simulation that aimed to map how human decisions might recursively interact with past choices to produce a self-correcting or diverging timeline. The experiment became known informally as the Borg's room, after a doctoral student wrote in their notes. It's like walking into a room of time mirrors, every choice reflects backwards. The core idea was deceptively simple. If you could simulate not just a person's likely future, but how their knowledge of that simulated future would influence their decisions now, and then rerun the simulation with that new choice in mind, could you create a loop? Could a prediction about the future cause the present to change in a way that alters the future, which then retroactively changes the prediction itself? They began with decision trees and Bayesian probability models, but the key twist was adding a feedback layer. Participants were shown detailed simulations of what their life would look like based on different answers in a psychological test. For example, if a person scored high on impulsivity, they might be shown a simulated future where they struggled with stability and regret. If they scored high on conscientiousness, the simulated path showed slower success but higher long-term satisfaction. The subjects were then asked to retake the test a week later. The results were strange. Many participants changed their answers in such a way that invalidated the original simulations. But when the researchers ran new simulations with the updated data and showed those to the subjects, a pattern emerged. People began looping. A subject might rate themselves as impulsive, see a chaotic future, then rate themselves as extremely cautious the next time, only to receive a simulated life of missed opportunities and regret. On the third attempt, they would often average out the extremes, leading to a simulation that seemed more realistic. But the kicker was that their actual behavior in the following weeks started aligning not with their self-image, but with the simulations they had been shown, even if those simulations were based on false or manipulated data. In short, seeing your future, even a fake one, can make you behave in ways that bring it about, and that behavior, when resimulated, can influence you again. Borges would have called it a library of mirrors. Physicists called it a behavioral time loop. From a philosophical angle, this echoed Nietzsche's concept of eternal recurrence, the idea that if you had to live your life over and over, you'd become responsible not just for your choices, but for their inevitability. From a quantum standpoint, the Borg's mirror room touched on retrocausality, the notion that the future can influence the past if information about the future is introduced early enough. But what does it mean for time travel? Unlike machines or wormholes, this experiment didn't claim to move anyone through time, but it did seem to create causal feedback, a hallmark of time loops. The subjects were not just influenced by their past or their predictions, they were influenced by what would have been futures that technically never existed. Some critics called it nothing more than a psychological illusion. Others argued that this is how all time travel would work if consciousness is the medium. If you believe that timelines are shaped not just by physical motion, but by choices, information, and recursion, then even a mirror can be a time machine if it shows you the right version of yourself. In 2016, the Tokyo team tried to recreate the effect with neural interfaces. Volunteers wore a basic EEG headset and were shown avatars representing future versions of themselves, rendered in real time using AI estimations of their likely appearance, behavior, and speech patterns based on their current habits. One volunteer, a smoker, saw a digitally aged, coughing version of himself projected in front of him. Another saw herself giving a graduation speech in a country she had never visited. When interviewed a year later, over 60% of participants reported that they had made changes in their lives specifically because they wanted or feared becoming the version they saw. In this way, the Borg's mirror room became less about observing time and more about shaping it. What makes it haunting isn't that it proves time travel is possible in the traditional sense. What makes it haunting is that it suggests every decision we make is haunted by its own reflection, that somewhere behind the mirror of now are 1,000 silent versions of you waiting to be chosen or avoided. If you walked into that room and saw all the versions of yourself looking back, would you recognize the one who made it through? Or would you keep adjusting the mirrors until you did?